All right, welcome everyone. We have got 224 participants here and counting, so we'll go ahead and get started. All right, so welcome everyone to our workshop today. We are here to talk about making conservation a California way of life and about how forthcoming efficiency standards could impact local wastewater management. My name is Molly Williams. I'm an environmental scientist with the State Water Board's Office of Public Participation, and I'll be facilitating our meeting today. So first we'll go over our agenda. So we have quite a lot on our plate today. We'll go over a couple of logistics for the meeting and how to participate. We'll talk about a little bit of grounding, some introduction and background on the efficiency standards. Then we'll talk about where we are with trends in indoor water use. We'll review methods and presentation of results. We'll also have a stretch break in between since we have a lot of information to cover. After we come back from the break, we'll answer more comments and questions. We'll have a panel discussion on adaptation methods. Then the State Water Board's Department of Financial Assistance will present on funding opportunities. We'll also have time, there's an asterisk next to each presentation, after which we'll have about 5 to 10 minutes to answer questions or hear comments about that particular topic. And we'll adjourn at 4 p.m. today. All right, so in advance of the meeting, you should have gotten a link to our speaker card form, which just allows us to get a sense of what questions are asked and who would like to participate ahead of time. We'll drop that in the chat in case you still want to participate, so we have your question on record. So real quickly, take a moment to look in the participants list and make sure that your name there reflects your first and last name and your affiliation, if that's applicable, so we get a good sense of who's here. Our chat is disabled today, so you won't be able to use that function, but we do have the Q&A feature enabled so that you can ask questions, even anonymously, and we may answer those within the chat function itself down in the toolbar, or we may choose to answer the questions live here. And anyone who wants to speak can be invited to do so. So you can use the raise hand feature to indicate that you would like to be called upon to speak. And for phone callers, you can press *9 on your phone to indicate that you'd like to speak, to raise your hand, and you can press *6 to then unmute yourself once called upon. All right, and then the final piece of information here is that the meeting is being recorded. So right now it's live, and we will be posting it to the Water Efficiency Legislation Program page after the fact. And that link is right there. Alrighty, so I will now pass it over to Chris to introduce the conservation team. Chris, you're muted.
Thank you. We've been doing this for 2 years. It still happens. Welcome, everybody. The Climate and Conservation team is in the State Water Board's Office of Research Planning and Performance. We're a small team working on many projects. We're the team managing 1668 S606 implementation at the State Water Board. We're also the group leading the water loss regulation implementation and implementing the board's climate change resolution and managing the monthly production and conservation data set. Today I'm joined by Charlotte Ely. We are also joined by board member Morgan. Board member Morgan, would you like to say a few words?
There we go. Good morning. Good afternoon, everyone. Thank you so much. Yeah, and thank you to all the participants for taking time out of your busy schedules to join us this afternoon on this important topic. You know, this year doesn't only just, it is not just going to be the 50th anniversary of the Clean Water Act. It also marks 50 years since the last time historic investments were made to the wastewater industry. You know, once again, we have those historic investments that have been made on the state and federal level, and really excited to hear from the Division of Financial Assistance later this afternoon. because of that, our wastewater infrastructure is aging. And though that there, it plays a role in today's conversation. The per capita residential and water use has been declining. And our wastewater industry has stepped up to this challenge over the last few decades to change the operations and also to make changes to the infrastructure. Sorry that the little thing came up there. And so, over this time, you guys really have stepped up to these challenges and have adapted. Water efficiency, it has many benefits. It saves water. It also reduces energy use on the drinking water side. And also, it has many benefits as our climate continues to change. We also know that as Californians continue to use water more efficiently indoors, our wastewater collection systems and treatment facilities continue to experience lower or more concentrated flows. This will continue to present operational challenges for wastewater facilities. We're mindful that wastewater treatment facilities and collection systems face these issues along with the aging infrastructure and climate change. So, today we're talking about policy that in 2018, part of response to the prior drought, the legislature recognized the benefits of further increasing water use efficiency and passed Assembly Bill 1668 and Senate Bill 606. These bills directed the Water Board to set standards, but setting those standards is still a long ways off. It may be not until late of 2023 that those standards come in front of the State Water Board for consideration. So those standards are not yet set in stone. We're here today to listen to you all, to gather information, to gain a better understanding of what these potential hurdles could be in the future. We're committed to hearing from you and continue to working with you on those standards so that it makes sense as we continue to move forward in this changing climate. There has been prior engagement that I would like to recognize. There were DWR working groups and workshops, conversations to inform us to this point. In 2021, the State Water Board contractors and staff worked with some of you all to gather information and gain an understanding of where we are today, to produce the documents that were sent out late yesterday afternoon, to initiate further discussions. The report was sent out. Please take some time to review the report, the additional documents, share your feedback with us, share additional feedback during this workshop. In the future, there will be additional opportunities for engagement. There will be an analysis of economic impacts on the standard. So the analysis that's out there is not the last time that we'll be looking at it. There will be at least one State Water Board workshop as part of the regular rulemaking process. There will also be discussions at the State Water Board meeting in the future, and additional opportunities for public comment. So as always, I'm always interested in hearing from you directly. Please continue to reach out. So with that, again, I just want to thank you all for your time today and your valuable input. Please continue to reach out to us, share your experiences and your knowledge. And so I'd like to turn it back over to staff and continue to learn today through this workshop and further engagement with our stakeholders.
Awesome. Thank you so much, Board Member Morgan. We are going to go back to the presentation now, and Chris Martinez is going to take over.
Thank you, Molly. Next slide. In 2018, the California State Legislature enacted two bills, Senate Bill 606 and Assembly Bill 1668. These bills established a new foundation for long-term improvements in water conservation and drought planning to adapt to climate change and the resulting longer and more intense droughts in California. The two bills amend existing law to provide expanded and new authorities and requirements to enable permanent changes and actions for those purposes, improving the state's water future for generations to come. Since 1668 and 606 passed, the Department of Water Resources and the State Water Board have been closely coordinating to carry out the statute's directive. DWR was directed to conduct studies and provide recommendations to the State Water Board, and the Water Board was directed to adopt new efficiency standards by summer 2022. Using the adopted standards, each urban retail water agency will annually, beginning in 2024, calculate what's called an urban water objective, based on the water needed in its service area for efficient indoor residential water use, outdoor residential water use, commercial, industrial, institutional landscape irrigation with dedicated meters, and a reasonable amounts of system water loss, along with consideration of other unique local uses, such as variances, and a bonus incentive or credit for potable water reuse. Here is an infographic showing generally how the objective would be calculated. Today we're focusing on the standard that could affect local wastewater management. The residential indoor standard is highlighted in red. As with all standards, the residential indoor standard will be implemented at the water supply level and will not apply to individual customers. Next slide, please. Intertwined with the regular rulemaking process is an independent legislative requirement that the State Water Board consider the proposed efficiency standards' effect on local wastewater management, developed and natural parklands, and urban tree health. We have been directed to identify these effects by May 30th, 2022, and allow for public comment on the potential effects. At this time, a written summary of the findings and the report is publicly available at the Water Board's conservation site. Before going over the results of the study, we want to remind everybody that the methods used to understand how the proposed efficiency standards may affect local wastewater management were extensively covered during the December workshop. The slides and recording can be found on the Water Board's conservation page. Next slide.
Thank you, Chris, and good afternoon, everybody. For those of you who have not sort of joined a webinar before or heard our team speak, my name is Charlotte Ely. I supervise the conservation team and just wanted to reiterate what Board Member Morgan said. Really, thank you very much for setting aside the time to join us today, to hear what we've done and to share your thoughts on our process so far. The very first thing that I wanted to do is just give a really brief recap on the results of the indoor residential water use study that the department provided to the legislature in fall 2021. So if we could move to the next slide, please. So this report both presented the department's analysis, it described the methods used, and shared the findings. It also included a recommendation that there be a different residential indoor use standard than what was defined in statute, one that more appropriately reflects best practices for indoor residential water use. The report was required by the 2018 conservation legislation and was intended to inform the legislature as it considers next steps. Some of you may be aware that there is currently a bill. The legislature is considering a Herzberg Bill 1157, and it reflects the recommendations that were made in the report. So if adopted by the legislature, the standards recommended by the department and the State Water Board would be implemented, again reiterating what Chris has just said, at the supplier level and would not apply to individual customers. This was a a huge undertaking by the department. It was informed by account level data from over 1 million customers supplied by 18 different urban retail water suppliers by the state. That data was supported and corroborated by service area scale water data from 157 urban retail water suppliers, representing the water use of more than 18 million Californians. The report was based on data from 2017, 2018, and 2019. And what it found is that based on those years, average residential indoor water use was 51 gallons per capita per person per day, GPCD, and that the statewide median was 48 gallons per capita per day. It also found that the 25% of households in California were already using 44 gallons per capita per day or less. We wanted to draw attention both to this report and also to some of the more relevant appendices that are included. So now on our website, we have not only a link to the report, a link to the appendices, but also specifically links to appendices I and J. Appendix I goes over the benefits and impacts associated with increased indoor water use efficiency, and Appendix J is a description of efficient indoor water use, which for context, based on standards here in California that are set by the California Energy Commission and performance standards set by US EPA through the Energy Star program, efficient residential indoor water use in California would be about 35 gallons per capita per day. So that's one of the numbers to keep in mind as we're throwing a lot of different numbers out at you today. Next slide, please. Here, just sort of quickly showing the recommendations made by the department and the State Water Board. They were that urban water suppliers would achieve an indoor water use efficiency standard of 55 gallons per capita per day by 2023, declining to 47 gallons per capita per day by 2025, and 42 gallons per capita per day by 2030 and beyond. Before passing the proverbial mic to Joe and Peter, I wanted to recognize that regardless of what happens with AB 1668 and SB 606, wastewater collection systems and treatment facilities may continue to experience lower and more concentrated flows due to code standards and behavioral change. Californians are expected to use water more efficiently indoors based on the 2017, 2018, and 2019 data that the department considered in the analysis. They projected that water use would continue to fall due to passive conservation, estimating that half of California would be at 44 GPCD or less by 2030. An important consideration when thinking about that forecast is that passive conservation does not take into consideration the effects of existing conservation programs or of the actions that people take when responding to a drought emergency. And some of those responses do lead to permanent indoor water savings. So before we take a look at the flume data, let's keep in mind that that data conveys what's happening, where the devices are located, but that it could be a bellwether of larger statewide trends. So as Californians continue to adapt to climate change by using water more efficiently indoors and out, it appears that we are starting to see changes faster than what was projected in the residential indoor water use study. And with that, I think we can move to the next slide. And Peter and Joe, if you could introduce yourselves, that would be great.
Sure. Thanks for having us, Charlotte. Can you hear me okay?
Yep.
Great. Well, great. We have 4 quick slides and we'll get through this quickly. But before we do, I just wanted to give a brief intro about who we are, who Flume is, and what we do, because it's relevant to how we collect our data and how we analyze it. So Flume manufactures this little device that's here in green. It essentially straps around an existing residential water meter. And these devices can be bought online, at Amazon or at our website. So homeowners can go and buy these devices. They're inexpensive. They're $199. And we also have partnerships with utilities. So we have a lot of utility programs where utilities will actually subsidize these devices as well. And consumers can buy these devices as low as $9 in some of these programs. So they're fairly inexpensive and widely available. So how does this work? So basically, once a homeowner straps one of these to their water meter, it starts to collect data off of the meter every 5 seconds. So we get very, very granular water use information off of all of these homeowners' meters. And then basically it beams that data up to the cloud where we can actually take that data and analyze it either at our level or in aggregate across utilities or geographies or across the state or even across the nation. So why do homeowners buy these devices? There's two main reasons they buy the device. In the West, the big impetus to buy this device right now is that water is scarce and expensive. So homeowners really want to understand how they're using water and where. So our device actually tells them every single minute how much water they're using and where that water is being used. So they can tell very quickly, if they get a high water bill, they can start to really understand why they have a high water bill and where they're using most of their water. And really they can actually make changes that matter. It's amazing how many people buy this device and then they see that it's, using 1,000 gallons every day to water their front lawn. They make changes very quickly. The other big value to the homeowner is that we also do leak detection. So if a customer has a leak, we'll let them know right away. We don't tell them 24 hours later. We tell them basically as the leak is happening. And why do utilities want to subsidize this device? For two main reasons. In the West right now, and I'm speaking specifically of largely of California and Texas and Arizona and Utah, Colorado, places again where water is getting scarcer and scarcer and the drought pressure is real. They want to give their customers a tool, utilities want to give their customers a tool that really help them, again, know where their water is going. So if a utility is saying, hey, you can only water once a week, or hey, I need you to cut your water use by 25%, it's really hard to do that if you don't have a device that tells you exactly how much water you're using. Like I said, we tell the customer every minute, but they can also look every hour and every day and every month and be able to see really how to cut back. And the second reason utilities really like our device and why they're subsidizing them is that once a large number of these devices are installed in a geographic area, and by large, I mean more than 100, we can really start to tell them what's going on in terms of indoor water use, in terms of outdoor water use, in terms of fixture level use. We can tell them average flush volumes. We can tell them average shower flow rates. We can tell them average clothes wash machine volumes. So we can tell them a lot of information that they really can't get in any other way. So now that we have a lot of these flumes all throughout California, in fact, we have about a little over 15,000 flumes deployed across California, we can really start to look at kind of trends across California. And these little blue dots all over this map show where the concentration of flumes are. They really, we have high concentrations of flumes, obviously, along the coast, because that's where most of the population is in California. But we also have a good representation as well in Central California. And in the less populated areas, we have flumes, obviously not quite as many. But we do have representation. These different colors here represent the different climate zones in California. And we do have really good representation all throughout California. And it's pretty representative to where, like I said, where the populations actually are. So let's start looking at some of the data that we're getting. One of the really important things to note is that to look at California on average, how much average water use is happening, is interesting, but I think this slide tells the story a little bit better of what's going on in terms of indoor water use in California. It turns out that people in Los Angeles use water differently than people in San Francisco, and use have different water use habits than people in Riverside, as an example. So what we did here is we mapped 3 different metro areas. We've got the Los Angeles area, the Riverside area, and the San Francisco area. And when I say Los Angeles, I don't mean the city of Los Angeles. I mean the Los Angeles metro area, which is actually a pretty big area that includes Los Angeles and kind of a lot of the outlying cities. Same for Riverside and same for San Francisco. San Francisco is not just San Francisco. It's the Bay Area. It's Marin County. It's a big area. So what we did for each of those 3 metro areas is we plotted the average indoor water use per capita since basically the end of 2019. And what you'll see here along the y-axis is indoor GPCD. These are some of the numbers that Charlotte just presented on her past slide. So we kept it in the same units. And then on the x-axis is basically time. And this ranges from the end of 2019 to basically 2 months ago, the end of March, so the end of the first quarter of 2022. And what you'll see here is that these curves are pretty similarly shaped. However, the magnitude is actually different. So Peter, I'll turn this over to you. There's some pretty interesting things on this slide. Actually, if you can go back 1 slide. Sorry about that.
I think they're trying to hurry us along. I
know. I promise. We only have 1 more slide after this.
Yeah, I'll skip the introductions and go straight to the data. So obviously what you see in March of 2020 is the COVID bump. That singular increase in water use was a result of the lockdown that occurred. More people at home, more water use at home by the folks. I think it's important to look at these data in the context of what Charlotte presented for the proposed water efficiency standards. So, if you think about moving down to a standard of 42 gallons per capita per day, a place like San Francisco is pretty much there. They're already operating quite close to it, certainly in the most recent months. Los Angeles is not that far off. They're approaching, there. Riverside is a little bit higher. So that gives you a sense of the range, but also certainly that level of water use is absolutely achievable across a large number of customers.
Yeah, and one other thing I think you can see on this slide is that the trend is down basically for all 3 of these metro areas, which I think is interesting. I think in the next slide, we'll see that it's kind of leveling off now, but it's definitely been a downward trend for a while now.
Yeah, let's go to the next slide and this shows the average across all of the flumes in California and it even goes back, I think, perhaps a little bit farther. So you get the COVID bump is even more pronounced, in this little bit higher resolution view.
Yeah, and again, if you get rid of the year 2020, which is an anomalous year, no matter how you cut it, basically the trend is still down. And I think these numbers largely agree to with the study that the state did. By the end of 2019, we were at a indoor GPCD of around 50. I think the state study ended at the end of 2018, I believe. So, we're largely agreeing kind of in that with those numbers.
And significantly in the most recent quarter, you see indoor per capita use actually dipping below 40 gallons per capita across the entire state on average.
Yeah, and I think this number, has been driven down a little bit too, Peter. We have, as I mentioned before, we have a lot of these utility programs where there have severe drought pressure, especially the end of last year into the beginning of this year. And there was a lot of mandatory drought restrictions for people that actually do have flumes. So I think this is a little bit reflected here, but overall, we are seeing that this indoor GPCD is coming down in all geographic California. All right, I thought that was all we had. I think we can go to the next slide.
Great, and we have a couple of questions here in the Q&A for you all. We'll just do a rapid fire so we can stay as close to on time as we can. Okay, so question from Laura Feinstein. Can Joe comment on average water saved per home with Flume and payback period for the device?
Yeah, it's a great question. And honestly, it's really different in different geographies and different utilities that we work with. In places like Marin County, it was kind of hard to tell how much savings was due to having flumes versus having mandatory drought restrictions and fines for going over, water use. Whereas in places like San Antonio, where there was drought restrictions, but they weren't mandatory, we actually saw high water users saving anywhere from 10 to 15% on their water use. And we have everything in between as well. So really it depends on the actual geography. And we've studied a lot of these different geographies, and on average, it's about 10 to 15% flumes are saving them when people are actually aware of how much water they're using.
Great. And Fiona Sanchez asked, what was the sample size used in the data shown?
On the California data, the very last slide that I showed, that was about 15,000 flumes.
Great. Decent sample size. Okay. Scott Lenning asked, what program or code do I refer to if I contact my water provider to get the Flume discount?
It depends on what water provider you have. The different utility programs work in different ways. Feel free to send me an email. And after this, I'm joe@flumewater.com. And I'll be happy to let you know if your utility participates in a rebate program. And if they do, I'll tell you how to access it.
Great. I just put that in the chat for everyone.
Thank you.
Okay. Let's see. There's a couple more questions. Can you state again how you got indoor use from a reading on a meter, which includes exterior as well, which could include exterior?
Yeah, so the way our device works is, as I said earlier, it straps to the actual meter. And the way positive displacement meters work is that there's a magnet that spins inside the meter. And we're basically reading that magnetic field as that magnet spins inside of the meter. And it turns out the velocity of that magnet actually correlates directly to a flow rate. So we can very accurately tell how much water is being used at any one time. And basically, we're recording those flows every 5 seconds. And then what we do is we use machine learning to actually determine what's actually indoor use versus outdoor use. And then beyond that, we then actually determine we actually break down the indoor use into fixture level, like showers and toilets, et cetera. And that's all done through some pretty complicated machine learning and artificial intelligence we have a team that works on.
All right, so we'll go ahead and move on. There's a couple more questions in the Q&A that Joe and Peter might be able to answer via text, so look out for that. Okay, thank you both so much. All right, and we're going to move on to our next presentation from Charlotte from the Water Board, and Eric Porce and Harold Leverins and Caitlin Leo.
Yeah, thank you again, Joe and Peter, for joining. And if folks have questions for us as well as them, please continue asking them. And as we have time toward the end of the workshop today, we can come back to them. So next slide, please. So just wanted to really sort of recognize that while the bulk of today's presentation will be considering potential impacts to the wastewater sector, there are lots of benefits to water use efficiency. As Board Member Morgan was pointing out earlier, it saves water, energy, and money. It also protects water quality. It reduces the need for infrastructure investments, and it mitigates rate increases. These benefits are going to become increasingly important as our climate changes, and for these reasons and more, it's really critical that we make conservation a California way of life. So in 2018, the legislature recognized the many benefits of increased water use efficiency with the passage of 1668 and 606, and that's why we're all here today. But before jumping to some of the the impacts that we're anticipating to collection systems and wastewater systems, just really wanted to recognize that there are some very strong benefits to water efficiency, which is why so many of us here on the call today have devoted our careers to this work. Next slide, please. So just in providing a quick overview of what this analysis did, I wanted to sort of show what we evaluated and what we did not evaluate. And when I say we, I guess I'm speaking on behalf at this point of the really excellent team at CSU Sacramento and at different UCs throughout the state of California. It was a massive undertaking, and they deserve immense credit for the hard work that they've done over the last few years. So even before describing this, thank you ahead of time, Eric, Harold, Caitlin, and the rest of the team for the really great analysis that you've done. So what did they do? One of the first really big pieces of this approach was to connect urban retail water supplier service areas to urban sewer sheds. This is something that hadn't really been done on a statewide level. There was some information in urban water management plans, but the extent of this effort was big, and there remains work to be done. But I think the researchers that we've worked with took a big leap in, I think, a longer journey. We basically ran, once we did that, for 335 wastewater treatment facilities in the state, for 410 collection systems that we could link to urban retail water supplier service areas, we ran different scenarios to consider, how making conservation a California way of life might impact these facilities. We modeled how changes in influent flow rates might affect operations. We looked at, whether or not these proposed efficiency standards might result in lower influent flow, might result in lower, sort of more concentrated influent flow, or both. The team used outreach to scope the analysis and then also to benchmark the findings. And lastly, they estimated prospective operations and maintenance and capital costs. The analysis did not do what already we've been, heard people asking us for, which is facility-specific analyses. So for wastewater collection systems, the analysis did not estimate how influent composition might change for a specific facility. For wastewater treatment systems, the analysis did not estimate how influent composition and chemical usage might change for a specific facility. It did not consider the capital upgrades needed for a specific facility with site-specific considerations. And for water reuse facilities, it did not estimate how facility-specific changes in influent quality could affect operations. Next slide, please. So this is the good work of research data specialist Marielle Pinheiro and on our team. And what we did is we looked at trends in dry weather influent flow across the state. And this slide presents those findings. This is data that was reported to the State Water Board through our SWRCB portal. So in most regions of the state, we're seeing that average dry weather influent volumes have decreased since 2013, which is the onset of the last drought. And the numbers that you see in either blue or red are showing the change from 2013. And for most regions of the state, you'll see that that number is negative. And so this corresponds with observed urban water use trends. So for example, based on the State Water Board's monthly conservation production data, we've saw that urban water use had decreased 16% from 2013. But while total influent volume has for most regions decreased since 2013. For some regions, the linear trend suggests an overall pattern of an increasing influent, perhaps reflecting some water use rebound after the last drought. Population growth, which is shown here in the black lines, can also be a significant factor when we're comparing influent volumes over an extended period of time. So you'll notice that the regions with increasing influent trends, that are that's those with the red line, have some of the fastest growing regions of the state. So in other words, while total influent flow might not be decreasing, it may be growing more concentrated. And we share this this context slide, I guess, to help make the point that many collection systems and wastewater treatment facilities in the state of California are already experiencing the effects of lower or more concentrated flows, and both, of course, can pose some challenges to the wastewater sector. And we'll hear later today from a few facilities that are contending with these issues. Next slide, please. So here we're describing the three scenarios that we evaluated to think about how the proposed efficiency standards may affect local wastewater management, which we sort of broadly considered collection systems and wastewater treatment facilities and reuse facilities. So these are our three scenarios here. And when we looked at impacts, we looked at what might happen in 2030. So under scenario 1, we assumed that the residential indoor standard would be what it was set in statute under that 2018 conservation legislation, that it would be 50 gallons per capita per day in 2030. And as we can see, that's quite a bit higher than what we're observing currently. And even it's about what we observed using that 17, 18, 19 data. So that was sort of the piece of indoor water use, 50 GPCD by 2030 under scenario 1. And then for the outdoor residential piece, we assumed that the outdoor budgets would be calculated assuming 100% of irrigable irrigated area at 70% of ETO. Now I know some folks have not been following the work, the ongoing work on sort of residential indoor, residential outdoor water use, and the residential standard for commercial, industrial, and institutional landscapes. And so we can go into this more later, but in the meantime, I just ask that you sort of appreciate that when we were looking at these scenarios, we were considering the indoor standard and the outdoor standard and the overall budgets that might result, and then the ways in which urban retail water suppliers might reach those objectives. We assumed that about 15% of all the savings would come from reductions in residential indoor water use, which is why it was important that we consider not just the indoor standard, but also the outdoor standard. So scenario 1, 50 GPCD for the indoor, an outdoor standard that is a 70% of ETO applied to 100% of irrigable irrigated area plus 20% of irrigable non-irrigated area. For scenario 2, which is the scenario that we'll focus on for the rest of the presentation, we assumed that after 2030, residential indoor standard would be 42 gallons per capita per day, and the residential outdoor standard would be a 62% of ETO applied to 100% of II and 20% of INI. And then under scenario 3, that the residential indoor standard would be 35 GPCD, the residential outdoor standard 55% of ETO applied to 100% of II and 20% of INI. Next slide, please. So this summary graphic is showing the percentage of wastewater treatment facilities that, due to AB 1668 and 606 implementation, may experience lower or more concentrated flows than what was projected by 2030. The 2030 baseline we compare the scenarios to is what we think future influent flows would be in 2030, absent the implementation of 606 and 1668. In other words, we took into consideration population growth and urban water use trends. So here we're looking specifically at scenario 2. And again, we'll continue to focus on scenario 2 for the rest of my brief presentation. As a reminder, that was 42 GPCD for the residential indoor standard, 62% ETO for the outdoor standard. In case folks are interested in the preface we made available on our website yesterday afternoon, we include a summary table for each of the 3 scenarios that we evaluated. So what we see here is that under scenario 2, 61% of wastewater treatment facilities may experience lower or more concentrated flows than what was otherwise projected by 2030. And that's that top line number that you see. And then sort of at the left, we see that 38% may experience lower total influent volumes. So this graph, that is the blue columns, specifically show the percentage of wastewater treatment facilities that may experience reductions of varying degrees. So under scenario 2, we're seeing that 10% of wastewater treatment facilities may experience influent flows that are 0 to 5% lower than what was otherwise projected for 2030. 22% of wastewater treatment facilities may experience flows that are 5 to 10% lower than what was otherwise projected for 2030. And half of all facilities may experience flows that are lower than 50% than what was projected for 2030. So that's the sort of the story on potential reductions in influent flows, that 38% may experience these lower total influent volumes. We also saw that 23% may experience more concentrated flows, but not necessarily lower influent flows. And this would occur because of continued population growth, for example. So this really is a first order look at which wastewater treatment facilities may be impacted and the degree to which they may be impacted. There are a lot of things to consider and some data gaps to recognize. I'll provide some additional context in the next few slides, and then the CSU team will be able to speak to some of the data gaps we've encountered. So next slide, please. So this is a summary graphic showing the percentage of collection systems that due to 1668 and 606 may experience lower or more concentrated flows than what was otherwise projected by 2030. We see here that under scenario 2, 62% of the collection systems may experience lower or more concentrated flows. 45% may experience lower total influent volumes. And here, sort of same way of reading it, we see that under scenario 2, 11% of collection systems may experience influent flows that are 0 to 5% lower than what was otherwise projected for 2030, so forth and so on. Half may experience flows that are 15% lower than what was otherwise projected by 2030. And 17, again, may experience these more concentrated flows, but not necessarily lower influent flows. And so once again, this is really a first order look at which collection systems might be impacted, the degree to which they might be impacted, and the CSU team will take a deeper dive in just a few minutes. Next slide, please. Before explaining this graphic, I wanted to recognize, as board member Morgan did, that wastewater treatment facilities and collection facilities are facing multiple challenges resulting, as the combined effect of not just, aging infrastructure, but changing influent characteristics, topography, climate change, and we recognize that changes in influent flow and higher concentrations from water use efficiency and conservation can exacerbate these operational changes. We recognize that that's happening, and we're seeing that, in some of the data too. That said, we thought it was important to contextualize the findings that we are showing in the previous slides. So again, those previous graphs compared a future 2030 baseline to what influent flows might be under scenario 2. Here we're comparing historic influent flows to the theoretical flows under scenario 2. For the 335 wastewater treatment facilities that we have decent data for, we asked how many times has influent historically dropped below the volume forecasted under scenario 2. So looking at the last 10-ish years that we have influent flow volumes for, we see that 33% have not experienced annual average influent flows akin to those under scenario 2, but that 67% have experienced equivalent influent flows at least once, and that 44% of agencies have experienced similar influent flows, at least more than 3 times in the last 10 or so years. And now we're going to pivot to a few examples. So if you could advance to the next slide, please, Molly. Thank you. So in this graph, we're showing a lot of different data points. So please bear with me. On the y-axis, we're showing influent in millions of gallons per day. And on the x-axis are years. The light blue line shows historical influent from 2011 to 2020. The yellow dashed line up at top is the volumetric design capacity. The purple dashed line represents where we estimated the 2030 influent flows would be absent 1668-606 implementation. And the black dashed line represents the projected influent flow under scenario 2. So comparing the black and the purple dashed lines, we estimated that for this particular facility, influent flows might be reduced by 5.9% come 2030. Note that this particular facility has already experienced influent flows equal to and below the volume projected under scenario 2. This doesn't mean that increased water use efficiency will be a walk in a park for this facility, but rather that the agency and its staff have worked through these conditions before and may be well equipped to manage and respond to the lower and more concentrated influent flows that are likely in the future. Next slide, please. So here, just sort of referring back to those previous slides, this facility that I just shared the data with for would have been counted as one of the 22% of wastewater treatment facilities that may experience reductions in flow under scenario 2. So in other words, in this instance, our analysis may be providing a pretty conservative estimate of prospective impacts. Again, 67% of wastewater treatment facilities have experienced annual average influent flows akin to those under scenario 2. This is in part due to the state's history of droughts, that climate change is intensifying, and that, of course, as we've seen in the beginning of this workshop, that residential indoor water use has been falling. Next slide, please. So here is another example of a facility in which historic and current flows are well below the projected 2030 baseline and the influent flows under scenario 2. Next slide, please. A few slides back, that big pie chart, we showed that 33% of facilities have not experienced influent flows equivalent to those projected under scenario 2. In this example, we see an agency where we may have underestimated the degree of impact. So note that our projection for 2030, the purple dashed line, is below historic influent flows. For this facility, reductions then greater than the 12.5% we estimated may occur under scenario 2 conditions. Or it could be that our population data was flawed and that our 2030 baseline and scenario 2 projections are off. Next slide, please. Maybe we could just advance one more. Here we go. So here's an example of a facility with wet weather flows exceeding even design capacity, but for which dry weather flows are well below those projected for 2030 and forecasted under scenario 2. I guess in sharing these, wanted to give stakeholders, specifically our wastewater stakeholders, an idea of the kind of analyses that we're running, what we're considering, and sort of we welcome the opportunity to continue to work with you to refine the data we have to make sure that we make the best policy decisions that we can. With that said, I'll sort of get ready to pass it over to Eric Porse and team, and just acknowledge that we're looking at quantities here, right? And as we'll hear, later in the workshop today, that these are also issues about quality and concentration. And with data regarding, changes in influent water quality, I think we'd have an even better understanding of the kind of challenges that facilities are currently experiencing and what they may experience in the future. So I guess that's it for me, and thank you again for your time. And I'll pivot now to the CSU team.
Thanks, Charlotte. I appreciate it. Hi, everyone. On behalf of the team, my name's Eric Porse. I'm here today with Caitlin Leo and Harold Leverance, and we'll be presenting our findings on primarily the task 5 reports, which were reports of environmental effects. But this was part of a larger project across multiple universities. And if we advance to the next slide, please. We had the scope, it was fairly large because urban water management touches a lot of different aspects of our lives in California. So we were evaluating effects on urban retail water suppliers, including costs and benefits and effects on low-income communities. We were evaluating effects on wastewater management, including conveyance, treatment, and reuse. We were evaluating effects on developed and natural parklands, and many of these have water that's provided by urban retail water suppliers. And then finally, we were evaluating effects on urban trees specifically. So the last 3 bullets were related to specific sectors of life in California that were identified within AB 1668 and SB 606 for evaluation. And then the first sector, urban retail water suppliers, were obviously the potentially directly affected sector from the legislation. So we evaluated both the environmental and economic effects. Today, we'll primarily focus on environmental effects and specifically on the wastewater management community. Next slide. We presented in December the full project team in a little bit more depth, but just to reiterate, this involved Sacramento State, the Office of Water Programs, Department of Civil Engineering, and Department of Economics, UCLA, Institute of the Environment and Sustainability, and Department of Biology, UC Davis's Plant Science within the Department of Plant Sciences, Urban Ecology Lab, and Humboldt State as well. Next slide. We discussed this also in more depth in December, so I encourage you to revisit that presentation. But just to kind of give a quick overview, one of the important aspects to consider as part of this analysis was not only what's happening now or what's happening next year, but what's happening in essentially 10 years from now. So because the legislation is being implemented through 2030, we had the task of evaluating what changes would occur through 2030. In order to do that, we actually had to understand what we call the baseline would be in the future. So this is, as Charlotte alluded to, the effects of the occurrences, what the situation would be in 2030 for water supply, wastewater management, urban landscapes, and so forth, in the absence of AB 1668, SB 606. And this is where these considerations came in of all the sociodemographic population changes that influence water use, drought, ongoing fixture efficiency from code and incentive-based replacements, as well as outdoor water use efficiency with turf replacement. And we were able to build on a lot of tools in doing this, everything from the residential end uses of water studies that have been done both nationally and in California, through to end use modeling studies, appendices that provided appendices to the indoor residential water use study that was published earlier or last year. And then also the indoor residential water use study results, actually. So we had to sort of compile all this together to figure out a method whereby we could examine what water use is now, look at the water use data now, and then forecast what that would be through 2030. And we did this through a combination of sort of industry standard approaches using end use modeling and statistical based approaches with through multivariate modeling as well. Next slide. We would take that baseline condition and understand and to sort of assume that that would be the projected demand through 2030. And then we would compare that to objectives of water use. And these would be the objectives derived from the standards based on the indoor and outdoor standards. So at the time that we started this work, there were no specific standards in place. So we actually examined a whole series of potential scenarios and developed tools to do this. And we could identify for each of those particular scenarios what the effects of the regulations would be. So there would be a certain number of suppliers in each of these scenarios that would need to implement reductions to meet compliance. And this would be anywhere where your future demand is greater than the sum of water use that would be included in their objective. It should be noted too that these would be projected objectives, that there are additional pieces of information and data that suppliers will provide over the course of the next few years to identify a full water use objective. So all that involves obviously an enormous amount of uncertainty. And then for suppliers where it would be projected that future demand would be greater than the objective, what mitigation and adaptation actions would occur. So we did a lot of outreach with the supplier community in California, looking at the potential portfolios of conservation. There's obviously been 20 years of work going back to the California Urban Water Conservation Council working on this. So these, supply demand management portfolios on the demand management side would include rebates and incentives, codes and sort of drought-based restrictions, education and outreach, water rates. And so these were all sort of considered, and we kind of identified a core set that we could model. And then when we had to identify what mitigation and adaptation actions would actually occur, we had to consider a number of constraints, and those included saturation rates of efficient fixtures, community constraints such as income and size, outreach with suppliers, wastewater managers, and landscape managers helped us to identify what sets of actions we would model, and then finally demand management costs and benefits. And we included and wrapped this all up into using a simulation and optimization framework to sort of identify least cost pathways for suppliers that would have to reduce, and that yielded the costs and benefits on the supplier side. Next. Once we would identify what suppliers would need to reduce water, then we could start to project to these secondary downstream sectors, including wastewater management. And within wastewater management, you have collection, treatment, and reuse systems. And so we had to consider these kind of linked effects. And coming out of the 2012 to 2016 drought, I think a lot of the evaluations and studies started to really emphasize how these were linked systems. And our job, we kind of saw it as our job to be able to try to put some further empirical work that built on that. And when we started this, however, we sort of looked around at all the different sources, and there really wasn't a statewide tool available to estimate quantitative impacts for wastewater facilities from these demand changes in water on the water supply side. So how people change water use influences obviously wastewater collection, treatment, and reuse. And there were a series of historical studies going back to the 1970s drought. These studies were quite good, and they took a case-based approach, but we were able to use these case studies to control for variables and identified some overall benefits for energy use reductions within the time period of those functions. And then there were a series of recent evaluations that were quite good, looking at changes in salinity, as well as sort of capturing large-scale trends across the state in collection and treatment systems, effects and impacts from the 2012 to 2016 water use habits during the drought. And then moving forward, we had to consider a way we could extrapolate this to all the potential affected facilities, including identify which are the potentially affected facilities within the context of environmental and economic impacts. And this is what I sort of affectionately call the messy data area, because there hasn't been a fantastic amount of integration of wastewater management data in the state to date. So we have a lot of excellent information that's used for various purposes, for water quality monitoring and reporting, for local and regional planning, but at a statewide level, hadn't sort of put these all together. And so data sets such as the California Integrated Water Quality System that looks at sewer system overflow and violations, as well as water quality monitoring, has an enormous amount of data in it, but has not necessarily been exploited at a systematic level for these sorts of high-level analyses. There's also the new volumetric annual reporting, which sort of hit the street during the course of our project, as well as a number of information tables within DWR's urban water management plans. There's other data sources, including the wastewater user charge survey. There's even data from the Department of Finance. So we had to try to put this all together to build on the past work to get to a more statewide picture of potential effects. Next. In order to identify, as I alluded to earlier, what changes would happen for wastewater collection and treatment, we would take the indoor demand reductions from suppliers that need to reduce water to meet objectives and sort of posit what wastewater generation and influent flow impacts those would be. And then we had to develop a network modeling tool to be able to move water between facilities with the best available information that we could. And this is really where the gap in understanding existed when the work started out from all the different agencies and entities involved 2.5 to 3 years ago. So from that network modeling, we could project through reductions that would occur under the scenarios of AB 1668, SB 606 compliance, with some assumptions about how suppliers would react for implementing mitigation and adaptation options. And then we could also look at what the baseline indoor reductions would be from ongoing efficiency and conservation. And the difference between those two would be the impact of the regulations. And this can be characterized through a number of different metrics. We developed one here, for instance, which we called the water use efficiency objective impact factor, which is just essentially a ratio of what the wastewater treatment influent volume would be in the future compared to what it be projected now. And you can also think about it for the future with scenarios versus the baseline, right? So you can develop a number of different ratios of this. And this would be sort of a high-level metric to capture who or which facilities or collection systems might have reduced influent flow. As we were sort of entreeing, it doesn't necessarily capture well the effects on concentration, but at least gives you a first-order way to evaluate who might be affected. And in the right-hand side, you can see sort of a diagrammatic representation of this network modeling that we attempted to implement. And in doing so, this was just Excel sheets and coding. And you can have a number of different scenarios. Here we show a scenario where there's 3 water supply agencies that would send their effluent to one collection system that might then send water to 2 different wastewater treatment facilities. Within the state of California, we have every configuration of this potential diagram you could think of. We have multiple suppliers to one collection and treatment facility. We have one supplier sending to several facilities. We have one supplier sending to multiple collection systems, sending to multiple facilities. And so this makes it very difficult to trace this all through. So on the supplier side, we built up good data for a number of years. And there actually is good data on the demographic and system characteristics for collection systems. But on the wastewater treatment plant side, what we ran into is that some of the tools that we had to describe this didn't link up. Next slide. Once we identify how to at least move water through these linked urban systems, then the question becomes, what's level of precision and accuracy can we project different types of water quality or water flow outcomes. And so this is a kind of a diagram of how we moved through trying to integrate these data sources, and should emphasize a lot more work needs to be done here. There's still some major pieces of data that could help to shore up what these kind of future projections would be, but it's at least an empirical tool that we have now. So if we use the California Integrated Water Quality System to identify the total number of treatment facilities, about 1,300. And then there would be facilities that have design flows from that system, about 1,000. And then you move to the facilities that are more likely to supply larger systems, retail or larger urban retail water suppliers, about 800 or so, with more than 20,000 gallons per day of capacity. So about this time is where we made it after about a year. And then after about a year, we discovered what we affectionately called the Rosetta Stone, which would be DWRs within urban water management plans has some excellent tables that provide the linkages, this network modeling. So then we were able to sort of bring together all this information, but the problem is the tables in DWRs 6.2 and 6.3 didn't necessarily use common identifiers with the other data sets that were reported. And so a lot of our effort then had to be trying to put this all together to the best extent possible to be able to get to project the potential effects at a system level. So we are able to kind of project through these coarse effects, but the data gaps such as population for wastewater treatment and collection systems, service territories, discrepancies in the linkages and the network modeling prevent a system-specific precise evaluation. There's some level of uncertainty in there. Now, in considering the water quality effects, as you can see on the bottom, from CWICS, it's a huge repository of information that's available. And we were able to derive for about 160 wastewater treatment plants of interest, specific time series records of influent flow and water quality that we were able to use, but we didn't have it for all of them. So we couldn't necessarily project water quality effects for everyone. And kind of broad scale outreach throughout the state collecting all this data was too large of an undertaking. So we had to use a combination of using all the data available and then some extrapolation that we'll talk about next. One note just to preface here that what my colleagues Caitlin and Harold will speak about is this, this consideration between lower flows and concentrations, which would be familiar to any sort of process engineer. So in this context, to project effects of wastewater management, we have to incorporate changes in flow, population, and concentration over 10 years and think about it in relation to where a facility is currently operating. What is its current design flow and average influent flow? Right, so if you're looking at changes between, say, 1 year, it's likely the population probably didn't change that much for that facility, maybe in some areas with growth. But if you're looking over 10 years, you could have significant changes in population. And on the left-hand side, in the bottom graph, you see a diagram of sort of modeled changes between the per capita flow on the x-axis, which would be per capita influent flow at the wastewater treatment facility derived from influent from collection and upstream suppliers. And on the y-axis, influent BOD and influent biochemical oxygen demand and suspended solids concentrations in milligrams per liter. So historically, if you go back several decades, and what we tried to frame in the reports is that facilities last a long time, right? We build infrastructure for a long time. And historically, the design metrics for influent flow were 100 gallons per capita per day, give or so. So if you had several decades ago a facility being designed for 100 GPD, and it was now operating closer to the left side arrow, which would be similar to the current water use standards at 50 or 55, you would have a corresponding influent concentration increase, right? So at 100 GPD, you might be designed to manage 200 milligrams per liter of the core constituents. And then when you reduce your down to 50 GPD or even lower, then that certainly increases. And on the right-hand side, you can see some evidence of this. So this is a probability distribution of influent flow concentrations at various wastewater treatment facilities for BOD and TSS with a mean of 320, which sort of aligns with our other understanding that current water use is around 50 or 55. So if we project forward through 10 years, we're considering population changes with either equivalent or lower flows, volumetric flows. What will be the consequences for concentrations and loading, since loading may remain the same or increase going forward, right? So all this in relation to where a facility is currently designed, this is really the crux of where wastewater planning has to connect with water supply planning in 21st century California in the future. Next. For the last slide, I'll discuss an effort that we had for outreach with the wastewater management community, and I'll next slide, please. And I'll thank all the clean water agencies, the industry organizations, so CASA, SCOP, BACWA, CVCA, and California Water Environment. And they helped us organize a series of outreach with some questionnaires, but also some evaluations and in-depth kind of interviews with particular facilities. And this was incredibly helpful for a few reasons. So one, this helped us kind of learn more about effects and see how those effects may have changed from some of the 2012 to 26 evaluations, if they had changed. It helped us to scope our analysis and put boundaries on what we might or might not be able to say. And it also helped us to benchmark some of the findings from these from sort of modeling and extrapolations that we were trying to do in what was a relatively compressed kind of research timeframe. So here you can see just two snapshots of results just from questionnaires. And so for wastewater collection systems, in the future, given current capacity of your systems, over what range would low influent flows require remediation actions? And this is really the crux, right? Because you identify what, a potential volumetric reduction or a change in concentration. What does the community indicate? Where would this impact really kick in? So for collection systems, you can see that between 5 and 10%, some respondents indicated this, but as you get up towards 20% flow reductions, then certainly there's some impacts kicking in. And for the wastewater treatment community, in the future, given current capacity of systems, over what range would low influent flows require remediation actions? Not as much at the 5 to 10% range, but certainly similar trends at the 10 and 20% range of systems and facilities indicating that there would be effects and adaptation actions, remediation needing to be taken place. And these remediation actions could take the form of process changes or capital upgrades. And within this outreach, we asked kind of lots of different questions about this to kind of get some more specificity on what was already in literature. So, just to highlight a few of the responses, and they're detailed in the report. So, for treatment systems, what were some of the operations and maintenance changes that might occur? Well, 61% indicated more electricity use, and that helped us think about the modeling on that end, but also capital requirements, corrosion effects on headworks, and so needing to replace or upgrade headworks, as well as changing out processes, upgrading processes as well. And then on the collection system side, it was sort of interesting, kind of summarizing, some themes, is that a lot of collection systems, we asked sort of, would you see no or minor or major effects to try to get a little bit of differentiation between those potential effects and operating challenges. A lot of collection system respondents indicated major challenges in the face of potential reductions. And so if you extrapolate this to how the current systems exist, we realized that we really need to focus on process changes in the collection system, which we had heard from a number of experts anyway. And so we went into depth to make sure we modeled that to think about how that would influence effects on the treatment plant. With that, I'll turn it over to my colleagues who will speak more about those topics. So you can advance the slide, and I'll let Caitlin Leo with Office Water Programs take it away. Thanks.
Thanks, Eric. Next slide, please. All right, so as Eric said, we wanted to take a look at the impact of the flow reductions on the collection system. So Some of the main low flow effects we were looking at were an increased deposition of solids, more frequent blockages in pipes and lift stations, increased hydrogen sulfide production, which would lead to an increase in odor complaints, as well as corrosion, as well as root intrusion and a reduction in pumping efficiency. And what we were really concerned with was the collection system responses to these impacts, such as increased labor, increased chemical usage, changes in energy use, and additional equipment needs, as well as increased repair and replacement, specifically due to the increased corrosion rates. All right, next slide, please. So in order to kind of put numerical values behind some of these effects, we developed an Excel-based model that essentially what this model does is it takes a lot of different equations and modeled processes available in literature and combines them into one model to have kind of a more holistic look at what's happening inside the collection system. So it takes a lot of individual processes that are pretty established in literature, such as flow velocity in the collection system, H2S production, and kind of combines them into one larger model. And how it does this is it takes very generic or general collection system characteristics, such as population, influent flow, miles of pipe size distribution, and temperature, and uses those as inputs, predicts the collection system influent concentrations, and then goes through and models some of the processes listed below. So flow velocities, H2S production, corrosion rate are some of the most important ones we looked at. And I think one thing that's important to note about this model is kind of a very conservative approach. So for example, when we were plugging in a temperature, we used a collection system's average summer temperature. So it is kind of a worst case scenario, which I think is important to keep in mind. All right, next slide, please. Okay, so some of the key outputs of the model were the average sediment depth, average corrosion rate, and H2S emissions per mile. And these were used to kind of estimate values for some of the responses we were talking about earlier. So annual chemical costs, annual pipe replacement costs, and pumping energy. So the model we were able to run for about 50 systems, and these were chosen based on data availability, as well as varying them by like population served, as well as the region in California. And once we ran the systems, we were able to plot each of the model outputs. So the percentage change in, for example, corrosion rate over the percent decrease in flow. And we ran each of the systems at their current flow and decreased it by 25% increments of 5%. And from these, we're actually able to get incremental changes, which you'll see on the next slide. Next slide, thank you. Oh wait, I'm sorry. But alongside of this, we were doing we used data from the SSO database, as well as some of the outreach responses to group the collection systems into clusters based on some collection system characteristics that we had identified as being like risk indicators. So the ones that we ended up grouping them by were the percentage of pipes that had a diameter of less than 8 inches, their climate zone, their current flow, and their average summer temperature. And from these, we were able to come up with 3 different groupings that basically assess the risk of each collection system. All right, next slide. So as I mentioned before, the model outputs, we were actually able to get incremental changes, which ended up being a lot more easily applied to the flow changes that were predicted. So for example, for collection system 1, for each percent decrease in flow, the model was predicting a 1.98% increase in corrosion rate and a 0.34% increase in H2S emissions. So we had these results for all 50 systems. And from there, because we weren't able to run the model on all the systems due to lack of data availability, as well as it being an Excel-based model, so it was pretty time consuming. So we were able to take the clusters that we developed before and assign each of these 50 systems to a cluster, and then create or average an average incremental change for each of the model outputs for each cluster. And this was really helpful because then we could apply this to the statewide collection system data. So next slide, please. So thank you. So we took these average incremental changes by cluster, as well as all the collection systems that were predicted to have flow reductions. And we grouped those collection systems into the clusters and then apply these incremental changes to their expected flow reductions. So the table here is the outputs for scenario 2. So each of these, these are the outputs for scenario 2. And so for each of the clusters, you can see the average change in each of the model outputs. So for cluster 1, on average, the systems were showing a 14.5% increase in H2S emissions, a 24.2% increase in corrosion rate. And then these numbers were used to inform the economic analysis and kind of take a look at what's going to change as far as operation and maintenance costs and capital costs go. And yeah, so that was how we kind of tried to put some numerical values behind the collection system impacts. And I'm going to turn it over to Harold, who's going to talk about how we did that for the wastewater treatment facilities. Next slide, please.
I think we're actually going to take a quick break since we're running a little over time, and want to give people the opportunity to stretch and take a bio break. So let's see, it's 2:30 now, just about, and I think Molly, we had a 10-minute break scheduled.
Yes, so let's come back at 2:40 and we'll resume with Harold's presentation then. All right, folks, welcome back. We'll go ahead and resume with Harold's presentation. Hope everyone's made their way back to their computers, feeling refreshed. So Harold, whenever you're ready, you can take it away. And after this, we will have time for questions.
All right, thank you, Molly. Next slide. So I'm going to continue with the discussion here, carrying on where Caitlin left off. And this part of the presentation is specifically about the impacts on wastewater treatment facilities following the collection system. A lot of this data was acquired through literature review and discussions with folks at wastewater treatment facilities. And the types of issues we heard about are summarized on the left under low flow effects. One example is an issue with grit removal. Basically, grit that's in wastewater is has a change in density due to more concentrated wastewater. It causes oils and less buoyant constituents to adsorb onto grit materials and makes grit less buoyant. And so what happens with more concentrated wastewater under low flow conditions is that grit carries through wastewater treatment plants and causes issues downstream and wear and tear on pumps. We also have issues with hydrogen sulfide, which gets carried along with wastewater collection systems, arriving at wastewater treatment facilities and tends to corrode the headworks. So we get increased concrete corrosion and metal corrosion at the headworks of wastewater treatment facilities. We're also aware of deterioration of activated sludge and trickling filter processes. Basically, as wastewater gets more concentrated, it's more difficult to treat effectively, and that the systems we designed to treat low strength wastewater have to be modified to treat higher strength wastewater. We're aware of increased ammonia concentrations and at wastewater treatment facilities that have to remove nitrogen or have to remove ammonia, that this is a big concern. We know about disinfection problems. Common types of disinfection systems in California are chlorine and UV. Chlorine disinfection is affected by ammonia and also dissolved constituents in general. So when you have higher concentrations of dissolved constituents and ammonia that are reacting with chlorine, we have to add more chlorine to the water to get disinfection. Similarly with UV disinfection, with more concentrated wastewater flows, there's more dissolved constituents that cause transmittance issues. Basically makes the water like a little bit darker in color. It's not really perceptible to our sight, but if you're doing UV disinfection, these dissolved constituents absorb UV energy and it makes UV energy less effective. So we basically, in effect, have to increase the amount of energy we're putting in for UV disinfection to disinfect wastewater. We also have increase in salt concentrations in the effluent. And that is a serious concern for recycled water programs where we're using this water for example, for irrigation, that some sensitive crops aren't able to deal with this concentrated wastewater with the salts or higher concentration. Higher salt concentrations also affect any type of downstream demineralization or further advanced treatment that we want to do. All requires additional energy when we're using concentrated wastewater flows. And finally, just an overall reduction in the amount of water that's available for water recycled projects, just due to sheer limitations of volume. And finally, some of the responses, these are similar to the responses we heard for wastewater collection systems. Increased energy use. We need more labor to manage these materials. And for example, the loading of solids we get flushing out of the collection system. Increased chemical usage at wastewater treatment facilities, a lot of times for odor control, but also for alkalinity or carbon addition for nitrogen removal. Increased wear and tear on pumps and increased repair and replacement needs, primarily due to corrosion. And increased need for process upgrades. Effectively, as like the wastewater changes from what it was designed to be or what it was expected to be, at some point, the processes need to be modified to adjust to the new wastewater strength. And finally, potential for revenue losses due to reductions in recycled water available for recycled water flows. Next slide. As Caitlin said, for the wastewater collection systems, we developed an Excel model, and we programmed in the various processes we thought that are relevant. For the wastewater treatment facility modeling, we use a different approach. We use a commercial model, in this case, BioWin, which is a commonly used model for simulating wastewater treatment processes. And what we did is we looked at the most commonly used types of wastewater systems used in California for larger facilities. And we looked at, for example, conventional activated sludge process. We looked at activated sludge process with ammonia removal. And we looked at an activated sludge process with total nitrogen removal. For these three model configurations, we looked at the influent we'd be expecting from the wastewater collection system models that Caitlin presented. And we said for these different wastewater collection system models and the spectrum of different influent concentrations that we might be expecting, how would that impact these different types of wastewater treatment systems that we're looking at? So we took the wastewater collection system data and we used that as an input to the wastewater collection treatment models. And we basically looked at different flow and concentration ranges. We put that through the simulation model, and we used the model to predict changes in energy or chemical usage. And we normalized that back to the flow rate. So effectively, we came up with solutions for different sizes of wastewater treatment plants, assuming that they started with a flow rate of around 100 gallons per person per day as a influent flow rate and an influent concentration range. And then we looked at how energy and chemical use is changing as we reduce the influent flows. From these data points we got at each of these models, we constructed curves that basically, if you look at the change of your influent flow, changing in flows and concentrations, we could predict the increase or decrease in energy required to treat for each of these different configurations. And as you can see in the diagram shown on the slide, we did look at the whole process considering the influent transformations, changes through the whole collection system. We looked at where pumps were used, where chemical addition is used. We also looked at solids management for the whole treatment process. Next slide. The results from the model, again, here are summarized for scenario 2 in the 133 facilities that we've been discussing. And in general, what we found is that about half the facilities are going to see an increase in energy use, and another half of the facilities may see a decrease. The increase is caused by increases in flow, but also increases in concentration. And in general, it looked like the increase in energy could be about 10% for most, for the half facilities that are affected. Facilities that might see a decrease in energy would be due to reduced flows and reduced concentrations. And that would be, could be relevant for some areas. And in those cases, the average change was about a 7% reduction in energy usage. On the right, we have a summary of the need for capital improvements. And effectively what we found is that at some point, as you reduce the flow rate or you increase the concentration going to a wastewater treatment plant, that there could be a need to actually upgrade the treatment process for the new influent condition. And what we found is that there's about 36 of the 133 facilities we looked at that had a relatively rapid rate of influent change that we thought would require a capital improvement for that process. Next slide. The types of capital improvements that we're talking about and why they're needed in general is because you're changing the influent conditions, either the flow rate or the loading effectively, that it increases the the need to upgrade these facilities. So basically facilities are reaching the end of life much faster than was expected because the design assumptions are changing from what was originally intended. So what we find is that old aeration systems basically aren't able to produce enough, provide air at a rate for wastewater treatment. And so basically old aeration systems need to be upgraded. We found that trickling filters basically have limitations about oxygen transfer that affects their ability for concentrated flows. We found that nitrogen removal systems can't meet effluent standards without increasing chemical addition or increasing pumping energy input. So systems that are having to remove nitrogen are especially at risk because of concentrated flows coming in, and which also increases the nitrogen and makes it harder to meet permits. And operation and maintenance needs are basically increasing proportional to the concentration of the flow. So basically, as the gallons per person per day decreases, the energy and capital input needs are increasing. And basically that the shorter lifespan for these facilities is increasing the life cycle costs, because a lot of times these facilities are put in maybe for like a 30 to 50 year planning horizon. And so if we're having to make changes after only a few years, after decades, then that definitely increases the costs for the life cycle of these facilities. Next slide. We also looked at water reuse facilities in the sense of the flow balance mostly, to see what facilities that are already doing water recycling now could see a reduction in their influent. And so as Eric presented earlier, if we just look at the baseline reduction in indoor water use, the estimate for that was about 21,000 acre feet of reduction just due to natural people's tendencies to save water. Comparing that to the scenarios 1, 2, and 3, we can see that as we get to the more extreme scenarios, that we could potentially start to see net changes up to like 45 or 62,000 acre feet over the 5-year period. And in terms of like overall water reuse, that's just a few % of total water reuse, but it is significant and it impacts a few facilities, in particular, the ones that are using a lot of their water already. Next slide. But it's important to compare the savings that we are going to see in total influent to wastewater treatment plants with the total savings of water supply that we're seeing in general. And so if we look at the 3 scenarios that we have here, that the savings we're talking about, for example, for scenario 2 is 500,000 acre feet per year in the year 2030. And if you compare that to how much water is potentially going to be diverted from recycled water programs, it's about 5% of the value. So overall, much less reduction in recycled water than there is in total water savings in the water supply side. Next slide. So just to summarize some of the key themes that we've discussed here, that the wastewater data we have is a big challenge in the sense that there's disparate databases that haven't been kind of integrated yet. And so that's one thing that needs to happen so we can really improve the quality of the data we have to work with here. Impacts from lower flows are extensive. They're already happening and they've been happening, and they're going to continue to happen, and the effects are going to be different at every site. Most wastewater treatment facilities have already experienced low flow impacts, and a lot of other facilities aren't sure what the future is going to be because they were never designed for what's going to be happening coming up. And it's the same thing for the collection systems, that there's a lot of negative impacts occurring with underground infrastructure, and that's a significant concern because of the cost to manage underground infrastructure. In terms of adaptation, there's already a lot of actions that are occurring, but basically that every facility could need to potentially be upgraded for more concentrated wastewater flows, and certainly it's going to require more energy. And that a lot of wastewater treatment facilities are reaching the end of their life faster and are going to need to be upgraded or replaced. And finally, for recycled water programs, that there's already some recycled water programs that can't provide the amount of recycled water that they plan to due to flow reductions. So this is already happening in California. And that the salt buildup in recycled water due to water conservation is already affecting the ability to use recycled water for irrigation in some areas. So these are all like a lot of large scale impacts that are going to have effects for a long time. Next slide. I'm going to hand this off to Eric to talk about some of the cost implications.
Thanks, Harold. So to wrap up our portion of the presentation, today we discussed a lot about environmental effects under the rubric of policymaking, but another task of the project was to evaluate economic effects, benefits, and costs. And throughout this component of the work with our wastewater evaluation, we had our economics team, including Jonathan Kaplan at Sacramento State and Eric Eschker at Humboldt State, working alongside our process engineering folks, which is incredibly helpful. And there's a lot of rubrics in the wastewater industry for evaluating costs, especially for a particular system. We do preliminary engineering reports and so forth. When you try to bubble and boil those costs up, given all the uncertainty that we've talked about today, it became more of a challenge. So we took sort of parallel but slightly separate approaches, looking at annual treatment costs. We were able to work from per capita spending derived from Department of Finance data, but thinking about how different process effects using unit costs from literature. And you can see that for scenario 2, for annual collection system costs, the third and fourth rows, the statewide average annual collection system spending would be estimated to be 1.1 billion for annual O&M and 1.7 billion for capital costs. And then within the scenario 2 evaluation, the additional kind of operations and maintenance costs derived out of the process modeling and unit cost framework was 5 million. And capital cost improvements for pipe replacement, increased corrosion above the baseline level, it's 40 million. For collection systems, a lot of them are old, they've been in the ground a long time. So trying to differentiate those effects versus the additional incremental impacts was challenging. And additionally, we weren't able to necessarily benchmark those modeling outcomes against literature very well. We kind of saw values that spanned the gamut. And on the top 2 rows for average annual wastewater treatment costs, across the state annually on O&M, if you extrapolate from per capita spending in the urban areas, it's 2.5 billion, and annual capital costs would be 4.5 billion. And they look like they've been increasing significantly in recent years, based on a few different kind of data sources. And then additionally, on an annual basis, maybe we were able to derive out of the modeling that Harold described was around $60 million in additional costs for operations and maintenance, and 270 million additional in capital costs. It's important to note that within the framework of the Association of for the Advancement of Cost Engineering International, AACE, which provides one particular framework you might be used in evaluating the precision with cost, which is something that the engineering and economics community deals with a lot with infrastructure. These would be class 5 estimates. So they would have wide ranges of 50% less up to 100% more, right? And it's based on the fact that we did not specifically do kind of design site-specific evaluations. There just wasn't the evaluation or time available. And additionally, these are sort of preliminary numbers as Jonathan and Eric put these into what's called the statewide, the SWRCB, the required document for regulatory impact assessment, has a specific framework for evaluating costs, and that's something that's sort of a conversation between agencies, between the State Water Board and Department of Finance. So we've been providing the numbers and providing a draft template with additional probably work to do there. So those get wrapped into sort of estimates of what it would be on an annual basis and so forth. So that's to come, but just some preliminary estimates about what costs would be. And that concludes our portion of the presentation. And I'll turn it back over to Charlotte. But before doing so, I'll just say thanks, and specifically to many folks in the wastewater industry that we were able to talk to and speak with. Thanks for your time. It was a busy several years during COVID, and I think we all need some recognition that we had a lot going on, and pretty much to a T, everyone still made time to speak with us. So thanks very much for that.
All right, thanks to the CSU team for those presentations. We'll go to a couple questions now. As a reminder, if you'd like to speak, you can use the raise hand function in Zoom, or if you're on the phone, you can dial *9 in order to raise your hand, and we can call on you to unmute yourself. But before we get into the panel discussion, I just want to catch on some of these questions that folks have asked. Let's see, and Charlotte just popped on. Let's see.
Could you maybe advance it to the next slide so folks can be reminded of the form that they can fill out too?
Great.
And
there's our stretch break slide. There we go. Okay. Okay, so Alex Mackey asked a question for the Sac State researchers. Reducing TDS is a priority for all parties. If lower flows increase the need for the WRRF to remove TDS before discharging, which technologies do you recommend to bring it down to meet the permit? And I wonder if Eric, Caitlin, or Harold is available to answer that question.
I can help out with that question potentially. I think generally TDS isn't like the regulated constituent that we're thinking about, and most wastewater treatment facilities don't remove TDS because you have to use something like reverse osmosis. So we wouldn't really be doing that unless it was absolutely necessary. For example, if we're going to drink the water again, or there's some other particular application that required high purity water. So basically, we just have to find plants and crops that can adapt to the higher TDS water, or find lower TDS water supplies to use in the first place. And also to think about the stuff we're putting into the water when we use it, because that's what's adding the TDS to the wastewater in the first place.
Okay, and as a follow-up related to TDS, Sarah Crable asked, have you considered collecting data on recycled water, chlorine residual as a contributor to TDS?
Yeah, generally for when there's chlorine added to water, it's relatively small concentrations, potentially like 10 or 20 milligram per liter, which would be kind of a high dose of chlorine. So I think chlorine does contribute to TDS, but it's a small contribution relative to other sources of TDS.
There were also a few questions in the Q&A chat that I think the CSU team might be well positioned to answer. One question is coming from Matthew Hoft, perhaps how you pronounce your last name. He's asked, what is the degree to ammonia concentration increase? Is it purely a concentration issue, less water equals less dilution equals higher concentration, or is more ammonia generated in the collection system?
I'll just respond to that briefly. This is primarily a concentration issue, like that the amount of nitrogen going into the collection system is about the same because that's coming from people, primarily from urine. And so it's basically the amount of water that's being added to dilute the ammonia or dilute the nitrogen. And that's why the concentrations are going higher to the wastewater treatment facility. There is additional breakdown and fermentation of solids in the collection system, but that's all nitrogen that would have got to the treatment facility anyway. And so this is primarily about concentration issues. Although we should mention that there's a lot of interest in bringing like food waste and other organics into wastewater treatment plants, which also goes to the anaerobic digester for gas production, but also increases the ammonia loading at the wastewater treatment facility. So there could be outside sources of ammonia in addition to what's going into the collection system.
Thank you, Harold. There's a couple questions here too that I think, Caitlin, I think you're starting to answer one of them, it looks like, in the chat, but perhaps you guys could, you and Eric could answer them verbally too, because they seem related. One from Alberto Martinez and another from, I think, Anthony Manzano, about with lower flows in the collection system, are we more likely to see SSOs due to these higher concentrations of various constituents?
I can
Yeah,
start.
so
Oh, go ahead, Caitlin.
okay. We didn't include like a prediction of an increase in SSOs in our analysis, but you would expect to see an increase in SSOs with an increase in like blockages and like pipe failures due to corrosion rate. So while that's not explicitly in there, like implicitly, yes.
I just want to add a little bit to what Caitlin's just mentioned, is that one interesting kind of factor that we didn't really expect, but we learned about during this project, is that when you have a drought outside and there's less water in the environment in general, that tree roots go looking for water also. And when we're reducing the amount of water we put on the landscape, for example, during a drought emergency, that increases the pressure for trees to find water at other sources. And a lot of times the wastewater collection system is a readily available source of water for trees that are located in urban areas. And so really when we're during drought and during times when we're reducing irrigation water for landscape, it forces tree roots into wastewater collection systems. And obviously wastewater collection systems are all different, but a lot of them leak. And the tree roots can find the water and they can basically get into the pipes and cause even more blockages. So a lot of the blockages that are going to happen in the future are going to be caused by tree roots looking for water.
And Alberto and Anthony, in the reports, the draft reports that are online, there's some discussion of this. We looked at some of the data that's available around the sewer system overflow violations, and used it to try to identify as a risk factor to correlate, to be able to predict that, which then could be turned into sort of, an estimate of a benefit or a cost. And it was hard to nail that down due to a number of different factors, but I think it would be something to examine further for sure, and look at trends over time. I think it's one of these areas where bringing together this information can help identify the sorts of actions that are working effectively to mitigate these effects that are, likely to happen, at least in some instances.
All right. Looks like we've covered a lot of the questions in the Q&A, and I think the CSU team is also responding via text. So we can go ahead and move on to our panel discussion. So let's go ahead and pass it off to Jamie.
Thank you very much. I appreciate the, let me see, make sure, thank you, Molly. Sharing my screen over here, I want to make sure you guys can see it. Can I get a thumbs up, yep. Molly? Yeah, yep. All right, good. Thank you guys for the time today to share some observations out in the field. My name is Jamie Farrow. I lead the climate energy reliability practice with West Yost, and West Yost is a water engineering firm, and our purpose, our value intention is to advance water resources for future generations. And I'm working together today with Wyatt Troxel, a longtime partner and mentor of mine, Matt Anderson from the city of San Luis Obispo, lab manager, and Vince Innes, the Director of Wastewater at Ventura Water. So just as a starting point, one of the things that I'd like to start off in terms of framing the discussion is for the entirety of this mega drought that we're dealing with. I've been working with over 100 water agencies and wastewater agencies, primarily in Southern California and Central California, Central Coast, dealing with the challenges through this drought that they're facing in terms of process optimization, aging infrastructure, increased maintenance and labor challenges. And essentially the analogy that the picture I'd like to paint for you is that what it seems like, what is really happening out there with wastewater agencies specifically is it's like driving a bus down the freeway with gunk all over the windows. With the aging infrastructure that most cities are dealing with the variety of challenges like drought and high strength sewage that they're facing and dealing with on a day-to-day basis, they very literally are barely able to see where they're going. And in fact, part of that is due to the lack of information in that Sewage database about influent quality, the lack of information that they have of their treatment plants about what's coming into the treatment plant. They have great data going out the backside on permit compliance and other challenges, but not a lot of good data going in. So one of our goals to help optimize the wastewater operations in the face of climate change and drought is really to clear off that windshield and provide a better visualization capabilities. But given the fact that high strength sewage and drought and conservation, that really just represents one chunk of dirt, mud on the windshield, right? There's a variety of challenges that they're facing on a day-to-day basis. And so to provide that clarity is really going to take kind of advanced tools and better metrics, better data visualization capabilities so that the bus drivers, the wastewater plant operators who are dealing with these challenges are better equipped to deal with the future. And that's one of the challenges that we see is just not a lot of really good data to help guide decision-making processes. And instead, we're seeing a reactive culture of dealing with problems as they come in, scrambling to fix the problems, not having a big enough budget to deal with all the challenges that they're faced with, and being compromised in how they deal with those challenges. So just quick kind of pulse check here. I wanted to spend a minute here. If you have your smartphone or your laptop handy, I'd like you to go to this website address or scan this QR code. And we're going to ask a couple of interactive questions. So while you're doing that, I'm going to just walk through this agenda here. Wyatt Troxel, as I mentioned at the top, my mentor and partner in crime here, is going to be providing a brief landscape sort of context on what we call connecting the dots and pixelating the view. We're then going to turn it over to Matt Anderson, who's the lab manager at City of San Luis Obispo, who's going to talk a little bit about what they're dealing with in their city, and then over to Vince to wrap us up. And I know we're as a whole, we're quite a bit behind schedule, but I checked with the organizers and we're going to try to stick with the allotted time here to give you the perspective of Matt and Vince. So if everybody has gone to the Mentimeter web page here, I'm going to just switch over to this screen. You can start to see some of these answers coming in already. So the question is, what are the major challenges to process stabilization or optimization that you face today? And think about the organization or the one treatment plant that you know the most about on the ground. Maybe not necessarily just agency statewide challenges, but what are the main challenges that we're facing here that keep you from being able to optimize? We'll just take a second to observe kind of what some of these trends are here. And this will stay live and we can come back and visit it later if we need to, if we have some time. But I see, and Wyatt, Matt, and Vince, please feel free to chime in here if you see things popping up that you'd like to comment on as well.
Yeah, do we need to advance a slide?
You're not seeing my Mentimeter screen?
I see the Mentimeter screen, yes.
Okay, so that's the first question that we're asking right now.
Hey, Jamie, I actually don't think we see the Mentimeter screen. I think we're just looking at the agenda.
Yeah.
Okay. Good, thank you. Thank you for letting me know. I'm going to really quickly stop that and share it better. I know what I did wrong there. Okay, now can you see it?
There we go.
So we're seeing the number one challenge that folks are commenting on here is treatment intensification, high strength sewage. These are the major challenges of process stabilization we're facing today. Supply chain constraints, process integration, lack of data is dropping. It started out pretty high, and usually I see this as a pretty high number. Let's go to the next question. You can still answer this after the fact. The next question here is, what are the likely process problems that you're likely to face in the future? So take a minute to think about these. These are ranked order: effluent compliance with your current system, lack of knowledge due to retirements, the great retirement, the great resignation that we're seeing, and coupled with the silver tsunami. Power reliability, there's reclaimed water infrastructure for more complete reuse is popping up there. There's a couple answers. So I guess this treatment intensification, maybe we're a little biased. We've just learned about a lot of great data that's being put together and advanced here in this issue. One of the observations I'll make is focused on some of the energy challenges that result is we've seen this occurring for the last decade, and the resulting process strategy is just more air, more aeration energy, more pumping energy. That's not necessarily a reliable and available power supply, is not necessarily something that in our future is going to be a foregone conclusion. We'll actually have to work to have reliable power supplies within wastewater organizations. I'll go to one more question here, and then we're going to turn it over to Wyatt. So what is one word that describes conditions that you don't expect to change in the future? This is a word cloud. If you just something that comes to mind, there's lots of change we've been talking about. What do you expect won't change? Wyatt, you want to navigate this word cloud as some of these things start to emerge here?
Sure. Well, certainly one of the things that won't be changing would be the laws of nature. Gravity is still going to be gravity. But certain things are going to change. Culture is changing. Habit patterns will be changing as much as we want to say it won't. So I think certain things are going to be much more dynamic. The one thing that isn't going to change is change. It's going to continue. And the question is, what's the response to it? So and I think it's really neat here that drought is sticking out. I come from a background that suggests that we're going into somewhere between a 250 and 500 year dry cycle, punctuated by wet moments. I think we should plan as if we're going to be in a perpetual drought, and if we're not, we're just lucky. It's going to be good. But if we don't plan for drought, our expectations are going to be crushed.
Yep. Well, thank you. Okay, I'm going to move on from the word cloud. Thank you for your input and contributions. That was a chance for us to sort of level set here and make sure we're all speaking the same language. Can you see the PowerPoint slide again where it says agenda at the top?
Yep.
Great. So moving along to you, Wyatt.
Okay, this is a visualization concept we came up with several years ago, is connecting the dots. We tend to drill in on specific items of interest, and in many cases, we don't see how these are interconnected. And so what I'm going to try to provide here today is just a very high-level concept of what we mean by connecting the dots and the significance of this, and use different analogies in that process. The one thing we only have just a very few slides. We don't want you to necessarily be making a whole lot of notes that are going to be hard to remember. But what we really want to do is give you some concepts and questions that might be hard to forget. And you're going to walk away from today thinking about a few things in a totally different way than what you're used to, using some very common vocabulary, but asking questions about it in kind of an uncommon way. So we want to leave you with good questions more than just good answers. So like one that I will tease you with is, think about this phrase, P cycle before recycle. What could that mean? And P has a double E in it. There are communities around the world, particularly in Europe and then in the Northeast, Maine, Vermont, areas of that sort, where they're doing urine collection in community infrastructures and treating it outside the treatment plant. That's an option that I have not heard discussed at all in California, with nitrogen being a big issue for treatment plants, and at the same time, fertilizer deficiencies, lack of ammonia and phosphorus for agriculture, which we're kind of heavy in. We're not thinking a whole lot about recycling nitrogen and phosphorus in our communities outside of the treatment plants, as well as inside. I've dealt with an inside plant capturing ammonia in various other chemical processes. That's very intensive, but these are passive systems to think about. So if you're curious about it, just Google the term P-cycle and see what you come up with. A couple of things I'd like to tease your intellect about your knowledge is we've talked about ammonia, nitrogen being in the collection system. First question is, what form is it in and what is it doing? Is the concentration increasing? And as one of the participants asked, are we generating it in the sewer? And the answer is yes. Some sewers, some collection systems much more intensively than others. Human beings don't put ammonia in the water. We put urea in the water and then it quickly converts to ammonia for the most part. That is occurring in the collection system, and the collection systems are also becoming biologically active. We talk about sulfide generation. Ammonia and soluble BOD are the brothers and sisters of sulfide. They're being generated as well. You just perhaps aren't looking at it. So we're converting protein, starches, things of that sort, into dissolved ammonia on the way to the treatment plant. The significance of it is if the protein, the McDonald's hamburger, enters the treatment plant, it will tend to settle out in the primary clarifier, go to the digester and be digested. The ammonia produced there can be captured. It can be dealt with in a side stream. If that hamburger dissolves, gets chewed up on the way into the plant and doesn't sink in the primary clarifier, there is no place to treat it other than the aeration or secondary system, which is energy intensive, and you have no control over that. So the question about managing the nitrogen, the conditions in the sewer, is where is the control point going to be? And is it going to be haphazard or is it going to be deliberate? So managing the collection system is a big ticket concept to think about. I'm going to couple that with one other term that we all think we're familiar with. That's BOD. Everybody can spell BOD. The question is, do you know what's in it? Because not all BOD is equal. You have particulate BOD and you have soluble BOD. As protein, which is BOD, breaks down in the sewer, it's generating ammonia, sulfides, and volatile acids, among other things. Think of like vinegar, acetic acid. The bugs love it. It becomes a soluble BOD that goes to aeration system and consumes electricity and capacity. Some of that stuff is not so friendly and can inhibit the process. But again, that BOD is breaking down, and the question is, do you know if, where, and when that is occurring? Because that should be part of a management strategy for both the collection system and the treatment plant, coupling them together. So connecting the dots, the lines in here could be collection system lines. One dot is the discharger, the other is the treatment plant. The question is what's happening in the transit through the line. So defining those conditions is really important. And as Jamie said, not only are we short on data on what's in the headwork, we're really short on data what's occurring in the collection system at various nodes or checkpoints. So with that said, in a little less technical terms, we have the sources of sewage. You have residential, which is the bulk of the wastewater coming into most treatment plants. That's regulated by toilets and showers and sinks and washing machines. We have commercial enterprise, which for the most part is carrier water. They're highly regulated along with industry, the next one, by the industrial pretreatment program, but the IIPP does not control residences. And so this stab with water conservation into in-house uses is indirectly affecting the residential discharge of sewage. Now, I want to say, I'm not saying any of this to be antagonistic to water conservation. It's absolutely critically necessary. The parallel with it, we have to be prepared to mitigate the effects of that going into a system that was not designed to be low flow. We are not ever going back to 5-gallon toilets. That's a fact. And in some cases, there we have no gallon toilets. We have waterless urinals. Our systems were not designed with that concept in the background. And as we go forward, we're going to see less and less carrier water. Most of the water going into the sewer wasn't sewage to start with. It is carrier water. It's what's moving the sewage to the treatment plant. And we're changing the physics of that movement based on the old physics of a collection system, low slope systems, going into a treatment plant in warmer weather that's becoming biologically active. So if we could skip to the next curve or graph, next one. So most people understand what this little curve is, the diurnal curve, which this is an imaginary representation. Each plant has a flow curve, and we're fairly used to thinking about the diurnal curve. And in some cases, there might even be more than 2 peaks, but there's the morning flush and the afternoon flush. What we don't think about necessarily is what's in it. That's the water flow carrying stuff to the treatment plant, BOD, nitrogen, metals, salts, all kinds of things, whatever gets poked down in the sewer and whatever's coming in through the carrier water. So the plants, for the most part, are designed for a hydraulic curve, an average and a min and a max. And this curve can be a daily, it can be seasonal. We have all kinds of flow curves. What we need are load curves. So next slide here is, I think we should intuitively understand that the concentration in that flow is not the same all day long. It's influenced by the demographics, the geography, and the habit patterns of the community. So we all think about, 2 o'clock in the morning, the little old men get up and pee, and then later they poop. So you have a higher concentration of ammonia coming in the early part of the flow, then you likely have a higher concentration of organics, BOD, coming in later. I think intuitively we understand that. I doubt that very many agencies are fractionating their sampling to determine what does this curve look like. Then it drops off in the afternoon. The lower flows are what we'll just call urban drool. It's leaky toilets, water, cooling water, whatever drainage might be occurring that's not really conveying sewage. So concentrations drop. That impacts the treatment plant. Then in the late afternoon and into the evening, in most systems, not all, you'll get another curve that is similar. People come home, they shower, they bathe, they cook, they wash, they do all kinds of things. So the nature of that bump in the curve could be totally different than the nature of the first curve. And the question is, what do you know about that? Because that second bump in the curve is usually when you're paying more dollars per kilowatt to treat. So that's where we start thinking about flow equalization or partitioning of the flow, storing it, flatlining that curve hydraulically and organically, and or managing the curve so that we can treat more of the organic waste when the rates are lower. Those are strategies that need to be built specific to each facility and demographic. Now, larger regional treatment plants, the mega plants, may not see a daily curve like this because the collection system is geographically so expansive and the curves get melded out in the tubing and the pipes coming in. Smaller plants, the smaller you get, the more pronounced these curves tend to be. And you'll see your DO sink like a rock. You got to kick up the blower ahead of or during one of these peaks to meet the BOD and the nitrogen demand for oxygen using conventional treatment. Okay, now I think a key thing to think about is if we go back to or go to the connected dots picture again, each one of those little nodes out there, think of those as being a household or a discharger, and specifically it's a toilet. And we're seeing concentrations go up. If we've cut the flush water in half, you would expect to see the concentration of the whatever constituent is you're interested in to go up. It would go up significantly. In the 50 years or so I've been in the business, I've seen the average sewage concentration double in the 50 years. Most of that's in the last 15 years. What I fully expect following nature's doubling factors is within the next 5 years, we will see it double again. It's not going to go 50 years. Within the next 5 years, and particularly with the enhanced and more aggressive water conservation initiatives, we're going to put less and less valuable carrier water in the sewer. And we're going to have to figure out ways to handle more concentrated sewage. That's going to require retooling the treatment plants, retooling our understanding of treatment process, finding new technologies, alternative technologies, and managing things better within the treatment plant. More enhanced side stream treatment, keep the nitrogen out of the main flow, keep it over in the digester loop if that's the case, using some other systems, elegant systems for nutrient uptake, whether that's through algae or chemistry or things of that sort. Those are options for us to look at. I think a key thing to understand is in those little toilets out there, you think about the advent of the waterless urinals. Do you know what the nitrogen concentration of urine is? I think most of you are going to say no, unless you went to med school. It's 200,000 milligrams per liter. It's very, very concentrated. And when we flush it, we start cutting it down. If we reduce the amount of flush water or the other amount of water that's blending in with it, we will likely see the concentrations move from where it was, say, 25, 30 milligrams per liter a few years ago to around 50 now, 45 to 50. It could easily go to 100. There is not a treatment plant in California designed to handle 100 milligrams per liter. Most of the designs are concentration based. They can handle mass load, but they're not designed to dilute a concentration like that. So if you have a BNR system, you're going to be hard pressed with conventional technologies to meet a future TIN limit on the effluent. If you have anything, say 75 to 100 milligrams per liter coming in, and I think we would be naive to think that is not possible. In fact, it's more like likely. It's going to be a big number. We need to be prepared for big numbers coming into the treatment plants. That's going to stress out the operators. It's going to stress the budgets of treatment plants. Cost of treatment is probably going to go up faster than you can raise rates. So you have policy issues coupled with practice issues and treatment principles. The designers are going to have to rethink design. Most of the stuff we're going to need to be thinking about and talking about is not in Metcalf and Eddy. Metcalf and Eddy right now is 20 years old. The technologies we need are not in there for the most part. There are good technologies out there. We need to find them and bring them in, and fairly quickly. So with that, I'll kind of leave it off there. I could talk about this stuff forever. But I hope I've teased you with some questions. I would hope that when you go back to your entities and your companies and whatever, that you start seriously engaging in a process of asking questions to find answers. Thank you.
Wyatt, you want to tee us up with the introduction to Matt and sort of really quickly
Sure.
hand it over?
Yeah, Matt is he's of a similar ilk of mine. I came into the industry through the laboratory door quite a few years ago. Matt is a lab manager with San Luis Obispo. It's a treatment plant, a mid-size treatment plant that's undergoing major improvements to try to stay ahead of the curve. And their treatment plant is going to get hammered. It's in a college community, but I think they can talk about what they're seeing real time in their treatment plant to help pixelate the picture a little bit better. So Matt.
All right, thank you, Wyatt. Yeah, so just to kind of dial in, our current facility is designed for 5.1 million gallons per day. You take the macro view, like Wyatt had mentioned, we have a community and city leadership that is extremely committed to water conservation. And they also don't hesitate to invest in any water, wastewater infrastructure. So we have a ton of support on that part. And then, yeah, as we kind of dive in to our facility, and this facility's been here one shape or another for the last 100 years. The current form was built in the 90s to take all of that influent ammonia and convert it to nitrate. And then in 2014, we received our next NPDES permit with the effluent limitation of 10 milligrams per liter of nitrate as N. And working with the water board, we were able to receive a time schedule order to kind of help us get through this period with an interim limit of 42.6 milligrams per liter. And then as I kind of go in here, the time schedule order is a tool to help us during this time. And we're having trouble meeting those limits. So I guess, do you want to go next slide? And, oh, you can back up one. Right, so yeah, just quick project timeline. Right, so this has been in the works since we received that new permit in September 2014. And just got a great email from my boss who sent me the process design and looking at the ammonia loading. Process design was last updated in 2018. And looking at our water quality data, we are starting to see the mass loadings of the new facility that's designed for 6.1 million gallons per day. We're seeing that mass in that 3.3 to 3.5 MTD. So good, go to the next slide. So yeah, that's one great thing about our facility is like the lab has always been kind of hand in hand with the operations team. We do support them daily with process control data, and then also with regulatory sampling and analysis. The graph on the left is our process control sample where we look at the composite nitrate concentration. And if you kind of look, we start in that 2010 range. You see that the swings go from about 10 milligrams per liter to 35 milligrams per liter nitrate as N. And then as you creep to the right to 2022, which I've just kind of snipped out here to prepare on that second graph, right? Now we see a range of anywhere from 40 to 60 milligrams per liter of nitrate as N. Go to the next slide. And then, right, this is, what does that look like flow-wise? So I pulled May 2010, right? The kind of quick eyeball estimate is we're somewhere between an average flow of 4.3 to 4.4 million gallons per day. And then if you look at the data from the first week in May here, we're averaging a little over 3.1 MGD. And you see it's also declining. All right, so next slide. So that's kind of our challenges at the treatment plant. And like I said, we're actively working on trying to gain compliance until we can have the new facility ready to go to meet our new nitrate limits. Yeah, so the kind of fun one here. So this is a pipe from our lift station that was constructed in 2014. And we had a complete pipe failure in 2018 with a replacement in 2019. The 2019 work was investigated in 2021, and it had to be warranted and replaced right within 2 years of shelf life. And got to give credit to our wastewater collections team, right? So they dug in to ask why. We did some hydrogen sulfide studies. The lift station where that ductile iron pipe was, we've seen concentrations of hydrogen sulfide on those diurnal swings that Wyatt showed us exceed 170 parts per million. So, right, the team then asked, why are we seeing those increased hydrogen sulfide concentrations? And then it's the upstream piping had a long retention time as Wyatt mentioned, right, you start to see those unsavory conditions that we don't want. And then once again, right, why do we have the long retention times? The why on that is we had a 10-inch pipe that was designed for more flow, which ended up being oversized, right? And then we just don't have the water to move everything downstream. Next slide, please. So like as Jamie was trying to say too, right? So what are we doing about this, right? These changing conditions. I have to give a lot of credit to our current and past supervisors, Chris Lehman and Patrick McGraw. So they've taken the database that we have been using and have turned that into a plant health dashboard. So that started with the operators identifying every key performance indicator for every single section of the plant, and then giving that a score and a weight. And so, as you can see, on this day, the plant was running at 98.8%. And so they break the plant down into the solids unit, the biological process, and then ultimately the disinfection process. So that 98.8 then turns into a Teams message, which you see at the bottom right-hand corner here, to kind of give that high-level view of why the plant is not performing at 100%. You know, as we kind of talked about before, right, that gives that common language to the whole operations team, and then also to the management team too, to see how everything is running and why it is not 100%. And then next slide. And so then this has been the next kind of step that's gone on this year, and I have to give the credit due to Patrick McGraw. And so they were able to take the real-time data provided from PG&E to see the energy usage at the plant. And right, so this is connecting that granular data of how they operate the facility to the energy usage that the plant sees, to the peak usage, and then ultimately, right, to how does that affect our PG&E bill that we see every month. And yeah, just trying to keep that in mind of that cause and effect and how to most efficiently run the facility. I think that was kind of it for what I had. If Jamie, if you had any questions, or Wyatt, you wanted to ask anything else or want me to go deeper, let me know.
No, I think that's good. I think we could ask you a lot more questions if we had more time, but I think that's a really great overview of the work that you guys are doing to manage these challenges. So thank you for that, Matt. And we'll hopefully have a few minutes for questions here at the end.
Okay, sounds good.
Thank you so much. Now, Vince, over to you.
All right, hello everyone. I'm not sure if you guys can see me, but anyway,
We got
okay.
you.
My name is Vince Inez. I'm the wastewater utility manager for the city of Ventura. Ventura is located about an hour north of Los Angeles, just in between basically Los Angeles and Santa Barbara. We're right on the coast, coastal community, and we're a population of roughly 100,000 people. The collection system is made up of roughly 310 miles of sewer pipe. We have 11 wastewater lift stations, and our average daily flow right now is about 7.5 million gallons per day. Our wastewater plant consists of primary treatment. From there, we go to aeration basins with for nitrification, denitrification, followed by secondary sedimentation, tertiary filters, and then we have some polishing ponds, and our final discharge location is in the Santa Clara River estuary. We do have a recycled water program that we have, which we provide recycled tertiary treated water to the golf courses in our city. And we also have a recycled water program for residents as well. So we have residents come into the plant, load up their tanks, and they're able to take that water home and irrigate their lawns or use it for other agricultural uses within the city limits. So we heard a lot of great information today from all of our other presenters, so I'm not going to go too much into depth of what I had planned on talking about, but we all know that there's a drought coming. This is the reality that we face with, and the reduced flows start in the collection system. When the reduced flows hit that, like Wyatt said, everything starts breaking down, causes odors, intense cleanings, more frequent cleanings, possible backups into in the collection system. So one of the things, there's an interesting fact that when COVID hit, our collections crew noticed there being much more grease buildup within residential areas where grease buildup normally wasn't an issue. So more people were at home, more people were cooking. So what we had to do was increase cleanings in those areas that they noticed. So that was, a lot of things like that came into play, really helped us take a step back and look at what challenges we're facing, especially in the pandemic. As wastewater treatment plants, we're always walking on that tightrope. We have aging infrastructure, we have process control issues. The change you might make upstream is going to affect what you do downstream. So you're always walking that fine line of what changes to make and how to change them, and making sure you don't upset the process in turn. You want to try new things and so forth, but that's kind of tough when you don't want to upset the balance that you have and have to maintain. One of the issues that came up for us, and it's a huge challenge, this last summer we were having we're doing a wastewater master plan, and we found out that our aeration basins, the structurally junk, right? They could fall down pretty much with a 4.0 earthquake, is kind of what we were told, which is pretty scary living in Southern California. Excuse me if I'm jumping all over the place here. So previously, we have a Ventura Water Pure project, which is we're going to take that tertiary treated water and use it for indirect potable reuse. So part of that is involved building an ocean outfall and then a advanced water purification facility on top of that for ground injection for potable reuse. One of the, it almost seemed like we were on pace for that. That was our future of our plant. And then it was like a big, punch in the face when we found out, hey, now we have to rebuild the wastewater plant as well. So our current plan right now to move forward is to follow suit similar to what San Luis Obispo is doing. We are going to build an MBR treatment plant and switch over from our activated sludge system and really change the whole dynamic of how we treat wastewater here in Ventura. Of course, that comes with a hefty price tag as well. So funding is always a huge issue. And it starts with outreach of not only city leadership, the community, but higher up as well. If you look at the photo of me, last summer, I had the opportunity to give the EPA administrator, Michael Regan, a tour of our facility, along with Congresswoman Julia Brownley. And they were very, very engaging. It was asking great questions and how much things cost, but getting into the ears of the big higher ups, to let them know, like, hey, this is our reality in California. We don't have water. We have to do something about it, and it's not going to go anywhere. In our line of field, when you ask somebody, hey, do you know what happens when you flush a toilet or when you wash your hands? The majority of people don't know, right? It just goes away. So outreach is really key on getting people on board and meeting people, talking to people, getting involved, and tours and a lot of outreach is really key moving forward. One of the other issues that I think wastewater plants are going to be seeing, especially with the low flow concentration, are issues from the APCD as well, the air pollution control districts. When you have a higher concentrations of constituents in the water, that leads to more odors and health risk assessments as well. I'm sure a lot of people out there know, they've had to comply with the health risk assessment or hotspots reports for the APCD, which are very very costly to put those reports together and then submit them. And it really is a long process. So that's one of the things that I haven't heard anybody touch on today, or impacts from that as well. One of the things that the city of Ventura has, we have a very aggressive pre-treatment program. We do what we call sector sampling. So we have 10 locations throughout the city of Ventura that were strategically placed to get a great representation of the sewer level, or the average levels of constituents within the collection system. We have one site specifically that's near a hospital, so we can monitor medical related constituents of emergent concern, to see what kind of impacts those will have on our facility as well. Wyatt has worked with us in the past a lot, especially with bioaugmentation. We had a big plant upset facility back in 2015, 2016 timeline where Wyatt came in and really helped us with that big influx. With water conservation really impacted our plant. So we started bioaugmentation in the collection system and here in the facility as well. So that has been key to really maintaining that level of compliance right now that we're facing. Yeah, with that said, that's pretty much all I have right now. I mean, kind of short for time, so I do want to be able to answer some questions if we can. So, yeah, Jamie, thanks for having me, and
yeah, no, that was great, Vince. Thank you for the real life example, and same to you, Matt. I appreciate it. So Charlotte, I know we were running out of time. I'll just kick it back to you, and you let us know where to go from here if we have any time for questions.
Okay, thank you, and thank you, Matt and Vince for being here and sharing your stories today, and Jamie and Wyatt for facilitating that, and sharing your experiences working with facilities like Acelo and Ventura. Because we bit off, I think, more than we could chew with our time here. I think I wanted to take a quick minute to just give people some tips on how to provide feedback to us on the report and the findings and the preface and everything that's now up on our website. We have uploaded a lot of material, onto the 1668606 website. I've put our conservation email in the chat, and just want to encourage everyone to take the time to look through the documents that we've made publicly available. This is the sort of first step in I think a larger conversation. So there will be plenty of time to let us know what you think. Please reach out to us. Send us an email, ask us questions. We focused on wastewater today. We'll be focusing on trees and parklands sometime in the next couple weeks. So thank you for sharing your time. And we'd like to, make sure to have our Division of Financial Assistance, hop on here and share with everyone some information about what sort of funding is available to specifically help with the kinds of challenges that have been described today. And after Sunny gives that presentation, I just wanted to let folks know that I'll be available, and other people from are available. Perhaps Jamie and team could hang afterwards as well. So with that, Sunny, will hand it over to you. And for those who can stay afterwards to chat, please too. I'm happy to have a broader conversation. And I guess one last note, if people are disappearing right at the hour, is that the rulemaking website is also where the recording of this workshop will be, as well as all the slides, as soon as possible. So if you do have to duck out at 4, you can always tune back in later to catch Sunny's presentation and any conversation that follows. So thank you all, and welcome Sunny.
Thank you, Charlotte. Once again, my name is Sunny Cowles. I'm a senior water resource control engineer. I oversee the water recycling funding program here at the Division of Financial Assistance. I'll be very, very brief because we are short of time, but hopefully it's still informative. If you're not fully aware of the Division of Financial Assistance, we do offer low interest loans and grants for a variety of different project types for primarily for wastewater treatment infrastructure and water treatment infrastructure. And we use state and federal funds to fund those projects. Now, as you can see here, so I'll go ahead and go over very briefly the funding programs that we have available, and then jump into the new state and federal funds that have been appropriated to us late last year. So as you can see here, the Clean Water State Revolving Fund is our largest loan program here. It's primarily for wastewater infrastructure and water quality projects. We have the capacity to fund about $600 million per year, and that's primarily through the federal CAP grant and our loan repayment stream. And that's similarly for Drinking Water State Revolving Fund. It's from the federal CAP grant and our loan repayment stream. And so we did receive some additional funds through the State Budget Act and the Bipartisan Infrastructure Law, or better known as the bill. And I'll go ahead and go over those later down the road in my presentation, but we did receive some additional funding. And so the Drinking Water State Revolving Fund, moving on, we typically can fund $300 million per year. And so again, some additional funds have been included for us to be able to fund additional projects. And the water recycling funding program, we offer grants and loans and grants through state funds. So that's state voter approved bond funds such as Proposition 1, Proposition 13, and Proposition 68. We also combine that with the SRF loan program to fully fund a lot of our projects. So it would be, most of our projects are a combination of both a water recycling loan grant and clean water SRF loans. Next slide, please. A few of our other funding programs here are the Safe Affordable Drinking Water Fund, which I won't go too much into these ones, but if you are curious, if you fall into any of these categories and you have projects for any of them, feel free to reach out to me and I can send you to any staff who are very knowledgeable about the programs. But there is a Safe Affordable Drinking Water Fund, the Drinking Water for Schools that has roughly $100,000 per school or $1 million per local education agency. There's a backup generator funding program, which has about $6 million authorized for funding. Next slide, please. And then there's the water and wastewater arrearage program. This was the bill relief program that was approved during the pandemic. It was about $985 million that was allocated, and it was given to the State Water Board to facilitate for any ratepayer that is having trouble paying bills. So that is a program. It's a newer program that we've included recently, but we do have that available. There's a stormwater program, and then the groundwater treatment and remediation program. Next slide, please. So as you may know, that late last year, the governor approved the 2021 State Budget Act, which approved about $1.8 billion worth of grant funding to the State Water Board. And now here's the split of that $1.8 billion. So $650 million of that went to wastewater projects, which is with a priority to septic to sewer conversions for DACs and SDACs. And the other $650 million went to drinking water projects with the priority to disadvantaged communities. $100 million went for the PFAS support for water systems. $350 million went to groundwater cleanup and water recycling projects. Now, it's good to note that here in the Division of Financial Assistance, as you may have seen in my previous slide, they are two separate programs. So we are currently recommending to the board to split that $350 million to both the groundwater cleanup and water recycling funding programs. So that would roughly equate to $160 million for each program. And again, these are grant funding for eligible projects. And it's also good to note that $350 million for the groundwater cleanup and water recycling projects is over a course of 3 years that began in 2021. And so we received the 2021 and we'll receive the 2022 appropriation. And then in the 2023 fiscal year, we'll receive the remaining portion. And then the remaining $20 million went to Mexico border rivers, excuse me. Again, the wastewater and drinking water funds, the $650 million for each, that was that has rolled out, so that is available for projects now. That was included in the amended IUP at the March 15th board meeting. Now the PFAS and the groundwater recycled water funds rollout is still in development. And again, we are working with the board right now with our recommendation to split the funding for groundwater cleanup and water recycling projects. But we do anticipate to have that funding available later this fall. Next slide, please. As you may know, that the federal government did give a whole lot of money for the federal EPA and the state revolving funds in the nation. It's better known as the Bipartisan Infrastructure Law, or the bill. These are for the California estimates, and they are for a period of 5 years between the fiscal years 2022 all the way to 2026. The bill included 7 different appropriations totaling roughly $6 billion. Now, 5 of those appropriations have actually been appropriated, and then 2 of them are for future, and they're subject to future appropriations, as you can see on the chart here. The $2.3 billion is for the future, and it has not been appropriated to the state yet. Essentially, those funds are for any eligible project, emerging contaminants, and lead service line replacement. The lead service line replacement is not a problem for clean water projects. So it's primarily focused on drinking water SRF, the drinking water SRF funding program. However, it's yet to we yet to see if we're going to even tap into those funds. So that's a discussion for the future. And so essentially, the funding will be made available once we request it in our application for the federal capitalization grant, and that is always included in the intended use plan, or what we call the IUP. And the next IUP will be released sometime in July. Currently, it's being drafted. I also did want to mention, excuse me, that with the bill came the Build America, Buy America provisions, which is going to be a heavy burden for some agencies. So if you are looking for clean water SRF or drinking water SRF loan funds using the federal appropriations, the BABA will apply to your projects. So it's definitely something to think about when you're developing your plans and specs for any future projects or applications. And I'm sorry that was a little quick, but thank you. So how to apply? If you'd like to apply for any assistance, you can visit our financial assistance application submittal tool, or also known as FAST. Everything is online, so go ahead and submit an application, and we'll receive notification and give your application to the right unit. There's also a technical assistance program, and the link is provided here. If you are a disadvantaged community or severely disadvantaged community, and you'd like to get some help figuring out where to start or how to apply, that's a great asset that we provide. Next slide, please. If you'd like to stay informed, you could always visit our webpage. It's continuously updated, or access our email subscription list known as Alaris, which sends out regular emails on any discussions or webinars, and it's a very helpful tool. And you can contact Christopher Stevens, our Assistant Deputy Director here at DFA. He has a wealth of knowledge, and he'd be happy to answer any questions. Or you can just reach out to me directly. I can provide my email address and phone number if you have any direct questions related to my presentation today, or funding opportunities.
That's great. Thank you, Sunny. And actually, at least one person in the chat asked for your email.
Sure.
So if we could pass that on to Alec, I think it was Alec Mackey. All
Sure.
right. So we talked about a lot today. We covered many different topics. You guys have heard from a lot of different, experts in the field, from academia, from wastewater operators themselves, from consultants working for them. We've got folks from our Division of Financial Assistance here, and then of course the conservation team within the State Water Board's Office of Research Planning and Performance. So a handful of us are able to stay longer and happy to answer some questions. I see that there are a few folks who are raising their hand and would like to sort of verbally ask questions. And so we can start moving to some of those, I think, unless Molly, you have a different recommendation. I will follow your lead, as I'm not sure how to actually call in people using the platform.
Great, thanks, Charlotte. So yeah, we're going over time here, but we're happy to stick around and allow folks to ask questions and comment. So we'll go through the speakers list here. There's 3 people who have their hand raised. You can also use the speaker card form. If you submitted a question through there, we'll try to answer those questions as well. Also, if you want to ask a question through the Q&A feature and indicate that you'd like us to answer it live, or if you'd like us to just respond via text, that would be useful too. So I'll go ahead and just call on the hands in the order they were received. So Matthew Fraser, you should get a request to unmute yourself.
Yes, thank you. I was actually wondering if there is any possibility of sending a cover letter or query letter to the Director Escobar of the California State Water Resources Board. I'm a District 4 Water Ambassador through Valley Water, and I'm also with EnviroCert International as a Qualified Stormwater Manager. So I'd like to see about collaborating on a project specific to municipal wastewater management and municipal stormwater management with the California State Water Resources Board.
Sure. I'll put in the chat the email of his assistant, Meredith Thompson. You can feel free to reach out to her directly. Matthew, thank you for your question.
Okay, I'm going to go to Steve Jepson next.
Hi, this is Steve Jepson with the Southern California Alliance of Publicly Owned Treatment Works, or SCAP. Thanks so much for a great workshop, very informative, lots of content. I have basically some comments, and I'm looking forward to additional collaboration probably at a later time. First of all, thank you to Eric, Caitlin, and Harold for an excellent presentation on the research that their team did on effects of indoor water conservation on wastewater facilities. There was a couple of comments I heard at the end of their presentation that I wanted to weigh in on. One is Harold made a statement that TDS is not typically regulated. Although we do have NPDES permits in Southern California that do regulate TDS discharges, and many recycled water agreements have TDS contractual obligations. And what wasn't touched on regarding salinity resulting from water conservation and the TDS effects of recycled water is when a recycled water provider cannot meet their TDS delivery requirements, they typically blend with potable water. So that is an and perhaps an unintended consequence of the water conservation is their recycled water agencies are going to need to blend or augment their supply with potable water, something that should be considered. And then Harold made a little statement about wastewater collection systems leaking. And you know, I think that can be misleading. Wastewater collection systems definitely have inflow and infiltration, particularly inflow, which is typically illicit connections or illegal connections to the wastewater system, or roof drains or patio drains, things like that. There are also sometimes defects, but they really don't leak. And there are some theories and statements about leaking, but there aren't studies that show that wastewater systems leak. And an interesting point about wastewater is it is very greasy and salty. And as Wyatt pointed out, it's getting more greasy and more salty with water conservation. And that grease or that biofilm results in a collimation layer that actually clogs up defects and seals the flow line portions of the pipe. So we just don't like to hear statements that wastewater systems leak. And then finally, my last comment, thank you so much for including me here, is Jamie and Wyatt's team did a fabulous presentation on those case study effects and costs. And I think that I feel like the costs are maybe underestimated by the research team. And a lot of that's probably because they got estimates from their surveys from folks. So, you know, the data you get, you interpolate. But I hope we have an opportunity for the wastewater sector to visit those costs and have a little dialogue with the research team to make sure they seem appropriate. That's all today. Thank you very much.
Thank you for your comments, Steve. It's nice to hear from you.
Thanks, Charlotte.
Okay, and I'll go to the other two people who have their hand raised, and then we'll go to the speakers list from the speaker card form that folks submitted in advance of the workshop today. So let's go to Gary Arunt.
Thank you. Senator Herzberg has Senate bill. This will lower the lower than in the current with respect to AB 1668. Has this information conveyed to the legislature? Is that this type of information is critical?
Gary, I'm sorry. It's a little hard to hear you. It's breaking up a little bit. If you're able to move or restate if you have a question.
Yeah, has this information been conveyed to Senator Herzberg?
That's better.
Senator Herzberg and the legislature concerning Senate Bill.
I think I can answer the question. I get the gist of it. Not specifically, Gary, but we can, through our Office of Leg Affairs, be sure to let them know that this information is available now, if we have not already. So,
well, it's timely because that bill is moving right now, and I just can't lecture a bit on this without understanding the cost and operational impacts of this.
It's very possible that our Leg Affairs offices have already contacted them, but I will double check. Thank you for the comment and the suggestion.
Yeah, absolutely.
All right. Thank you so much, Gary. We'll go to Jared next, and Jared Voskuhl, I believe that you also submitted a speaker card form. You should get a request to unmute yourself.
Hi, good afternoon. Thank you, Molly. This is Jared Voskuhl, Manager of Regulatory Affairs for CASA, the California Association of Sanitation Agencies. CASA represents more than 125 public agencies and municipalities that engage in wastewater collection, treatment, recycling, and resource recovery. And our mission is to provide trusted information and advocacy on behalf of California clean water agencies in order to advance public policy and programs that promote our community's efforts in achieving environmental sustainability and the protection of public health. At the outset, we want to recognize, appreciate, and agree that water conservation must be a way of life, given drought, climate change, and growing populations concurrent with decreasing supplies. We also would like to thank the board staff and teams of researchers and the presenters today who are all working on these issues. The presentations have been very detailed and exhibit the high quality analysis and the depth of the evaluation the board's undertaking. The staff's accessibility over the last few months since the December workshop also should be recognized, as we are very appreciative of the dialogues and conversations we've been having. And also just the report out on the impacts and the qualitative identification of those has been very thorough, and we appreciate the rigor of that work. Jamie and Wyatt's work on the, in the field experiences really seem to indicate really tangible impacts that weren't, hard to do justice to when you're abstractly or theoretically talking about what the impacts are. And it kind of led me to think what Steve Jepson previously said about the cost maybe being underestimated. Hearing about a pump station that had only 4 years of life on the pipes before corrosion had their impact. I don't know if that kind of, anecdote is really captured in some of the anticipated impacts. And so it would be very good to have more members from our field working side by side with your team as we're kind of exploring this and settling on those economic impacts. I'd also want to just reiterate that we're very interested in the network modeling efforts that were discussed by Eric, and we would like to collaborate further to get a better understanding and increase our confidence in the evaluation and identify those system-specific impacts per service area. And we understand there are data gaps at this time, and we think through a concerted outreach effort, we could probably supplement a lot of the existing data and overcome those issues to advance a more precise evaluation. And then moving on to just a few observations on the slides, and these are pretty preliminary because it's the first time I was seeing it today. But a few thoughts. One, on the economic cost, it appeared that there's an additional 300 million in annual increase for collection and treatment capital projects under scenario 2. If that's right, on the 10-year timeline, that'd be about 3 billion in new cost. And then on the O&M side, it was about 65 million annually, if I understood the table correctly. So that'd be about 650 million. So you're in that 3.5 to 4 billion range. And we're kind of thinking these might be conservative, underestimates. And that's still pretty sizable for the change of going from scenario 1, where we currently are with the legislature's indoor standards, to this scenario 2. So I wanted to flag that, and I'm very appreciative of all the work DFA is doing to get our members the resources they need to do this. But a lot of this might be O&M, and sometimes, I think, if I understand it right, a lot of the DFA resources may not be able to go towards those efforts as readily as they could for capital costs. I'd also like to note, in terms of the impacts to the collection systems, there was a slide that talked about only 11% having an impact if there was a 5 to 10% decrease in flow. And that kind of, I felt like, minimized potentially how it was read, because there was another 11% in the 10 to 20% reduction in flow. And then, combining those, that's 22%. Well, then the only other known impacts were for changes in flow that were greater than 20%. And that respondents, that number was at 20%. So you have more than half of the respondents who know what the impacts are saying they're going to have impacts between 5 and 20%. And so I wanted to flag that the way I was kind of reading that one. Also, there was another chart talking about change in flow, and it seemed like a 5% change would increase corrosion by 10%. And so I think the change for the 2025 target on that indoor standard is 12%, and the 2027 target is a 16% change. So there you're looking at a 24 and 32% increase in corrosion, if I'm reading that right. And that's pretty sizable and significant. And hearing about this story at the pump station earlier, it does cause concerns. And then the last observation was just from the flume data and some of the regional variation about water usage. It felt notable, as it seemed like areas with more supply are using less, and areas with less supply and that import water are using more. And I think that's an interesting paradox, and it probably bears further investigation as the state and the EPA and the legislature are all wrestling with where to land on this indoor water use standard and the overall water use objective. And it leads me to kind of, I think, take pause about whether we do something on that 2030 number right now. It seems like we have a lot of time and it might be premature. And especially giving some of these impacts to recycled water and how we're going to be relying on recycled water to augment decreasing supplies elsewhere. I think, I know it's not the board's decision, but it seems like there's a lot more to be seen before we really need to make a determination such as that. And so last,
okay, Jared, sorry. Thank you. We'll have to move on. It looks like Wyatt wants to respond to you here quickly on some of your points. And if you have further comments, we encourage you to email the conservation email account. But we're just short on time here. We want to make sure everyone who would like to speak has time to do so. So Wyatt, would you like to quickly respond?
Just a comment, and I think one of the comments he just made is interesting, and it brings up an appropriate question on the analysis of collection systems. I think we need to understand that the materials of construction in the collection systems are not all the same. And so unless you define what the material of construction is, you're going to have a difficult time qualifying the answer that you're given when you say, are you concerned about corrosion control? So smaller systems that are predominantly PVC pipe, they don't have a corrosion problem. Doesn't mean they don't have an odor problem, but the pipe is not going to corrode. And so they would tend to say, no, I don't have a corrosion problem. If they've been coating their manholes and or pipes, they would tend to say, no, we're not having a problem because they've been dealing with it probably for years. So I think one of the things we should parse out in the data set is how many of them already have a corrosion control program in place and or a system that's not prone to corrosion. Now, that said, that's important to the collection system, but even slow-moving cooking sewage in a PVC line, it may not affect directly the integrity of the piping system, but it is going to get transported to the treatment plant. And so the question then is, are you seeing impacts on the treatment plant with and without corrosion control? So it's another set of questions that perhaps we could look at developing an appendix for. Thank you.
Thank you, Wyatt, for that response. Oh, go ahead, Charlotte.
Thank you, Jared, for your comments, and we can find some follow-up time to meet and talk about the specific questions that you have, because it sounds like there's quite a bit there that you were trying to cover, but we can find more time later to discuss in greater detail.
Yes, thank you again for all of the great information that you shared, great ideas. Okay, I'm going to go to Mike McCullough next, who submitted a question in advance. Mike, would you like to ask your question to the group?
Yeah, certainly. So the question I had was that, we've been recycling water for 24 years for agriculture, and then we've just embarked upon some indirect potable reuse water recycling. And, obviously our agency has seen the trends of wastewater going down. And flows kind of stabilizing right now, but if the Senate Bill 1157 is passed, most of our flows coming in are residential, and so then naturally we're going to see a reduction in flows that come into the plant, which means we'll have less to recycle. And so it kind of goes back to some of the points that some of the speakers have said, is that you're going to have a reduction in volume, and then you have to maybe blend back with potable, but that's kind of defeating the purpose, because one of the areas that we provide recycled water to is a severely overdrafted seawater intruded groundwater basin that is critical, according to the GSA folks. And then we'd be having to pump more out because we don't have enough recycled water supply. So I think this is, kind of a case-by-case basis as we move forward, in our opinion. And, we're just kind of concerned that, one size fits all could be a little problematic unless there could be some relief, through the variance process. So I really appreciate the time, and thank you for taking my question.
Yeah, thank you for raising, those important points, Mike. I think sort of going back to the very beginning of the presentation, we shared an infographic that attempted to explain, how the objective would be calculated for each urban retail water supplier in the state. And I think one thing that's really crucial to keep in mind as we're talking about this is that urban retail water suppliers are going to be held to the overall objective and not any individual standard-based budget. So if it makes a lot more sense for an agency to invest in saving water outdoors as opposed to indoors, that's where their energy can be focused. And so while the 42 GPCD, may be the standard that the legislature, ends up, putting into code, it is not that 42 GPCD that and the resulting budget that every urban retail water supplier in the state would have to abide by. So I wanted to make sure that you were clear on that, because I know that there's been a lot of confusion around that particular topic. Second, we didn't talk much about the variance process, but as part of the new Making Conservation a California Way of Life framework, there will be variances. There are quite a few that were identified in statute, and the Department of Water Resources has, I think as of fall, made their draft recommendations available. So if you want to follow up with our team directly, we can send you more information about those variances and what they are, but relevant to residential indoor use, or things like significant quantities of water used for evaporation coolers within your service area. But there are a number of them. So variances are another source of water that could be added to the objective. So anyway, 2 points just in response to the concerns that you've raised there, and also thank you for your comments.
Eric, looks like you've got your hand up. Go ahead.
Thanks, Molly. Yeah, and Mike, I answered a few questions in the chat related to this, so we didn't get to go into all the details about modeling and results on the water supply agency side, but I think your point highlights that we need to start, working more across systems, and some folks are already doing this for sure, and then others, there's more to be done. So within the DWR-led indoor water use report that was released in 2021, there's an appendix done by MQ David Mitchell, a really nice analysis of end use modeling at the county level that just incorporated this kind of assumptions of background conservation, what they call it, but it's essentially code-based improvements. And that was looking as if, improvements in toilets and clothes washers and so forth. And if you project out, a number of years, it was somewhere around 45 or 46 gallons per capita per day is the indoor. And we sort of implemented this kind of approach for supplier specific. We used all this parcel data. I alluded to it, but we didn't get a chance to talk about it. And so our modeling looked at, overall mean, median per capita use in the absence, just the baseline, we'd call it, around 45 gallons per capita per day, give or take. It's detailed more in the report. And I think this, another aspect we didn't get to talk about is that in projecting what folks would do, we use this kind of least cost modeling approach. But wasn't ready by the time we had to put some of this information on paper for the environmental effects report. So we had to make an assumption based on what we heard from suppliers that only about 15% or so of the additional actions that they might undertake to comply would come from additional indoor use. And this is really because there's a recognition in that community, I think, that for folks who have been investing in this, in indoor water use efficiency for a long time, toilet improvements and so forth, that it's getting harder to find, older toilets to replace. So, your points are well taken about considering these trade-offs, but I would also note that I think we have a lot of work to do in the water management community to plan across these systems, to make sure that we're incorporating the, what folks on one side of the one sector are seeing, and how that's going to affect the downstream sectors in the absence of these regulations. And then add in the regulatory changes, and that makes it even more complicated and more uncertainty for agencies. So it's certainly a vexing problem, but I would say that even in the absence of kind of statewide regulatory changes, we're probably going to see, less effluent available for recycling in a lot of parts of the state.
All right, thank you, Eric, for responding. The last person who's still here on the call, looks like, who submitted a speaker card question is Andrew Kanzler. Andrew, would you like to ask your question?
No.
Okay.
Sorry, I was just listening to all the questions.
No problem. I can read. I think it's interesting. I'll go ahead and read it aloud. It's about whether the change in inflow is due to people returning to work. I wonder if anyone has any insight on that.
Actually, that question was answered already earlier on, because I asked it in the chat as well. Sorry.
Oh, awesome. No problem. Hard to keep up with all the questions.
Yeah.
Okay, Wyatt, you've got your hand up.
Yeah, I would like to make a comment on that, in that I think one of the things we need to understand is the population shift that occurred and is still occurring during the pandemic and the post-pandemic, if in fact we're safe to say that. There, in some places, their flows went down because people left. So in a sense, this portion of the population, perhaps small, out of the Bay Area and Central Valley, when people didn't have to be in an office building for work, went to their second homes in the hills up in the Tahoe area. So like I live part-time in Truckee, and in a 2-month period, the population of Truckee doubled. And so there was an influx there that's really impacted their infrastructure, both hydraulically as well as just social infrastructure. Markets couldn't supply enough food. Gas stations didn't have enough gas just because of the increased demand. And at the same time, those people came from somewhere. And they're living in their nice second homes up there. Then all of a sudden winter hit and they didn't know how to cope with snow. So they went back down the hill. And so I think what you saw perhaps in certain locations is a temporary decrease in flow and then a re-increase when people went back home. Now, some of those have stayed, but there's definitely been a demographic shift that is impacting some communities more than others. And I think the COVID impact is significant. Not only did the parents stay home, but the kids did too. And so that changes a lot of flow characteristics in a community, that you just can't look at a flow necessarily and figure out what the population does. And I think it gets to the question is, how do you recalibrate, or how do you keep the population count calibrated under these dynamic conditions? You have to make an assumption on population, and that assumption maybe doesn't accommodate the dynamics of the community. So that's a really difficult issue to deal with, but I think it's very real at the same time.
Thanks, Wyatt.
Thank you very much for that.
I wanted to flag a question for the CSU team that Laura Feinstein has put in the Q&A. I think it's one that would be really useful for for the remaining 73 attendants on the call and whomever is watching this workshop later. But perhaps Eric, you could respond?
I also
Sure.
invited Laura to unmute herself as well.
Oh, sure. Laura, go ahead if you want to ask the question.
Sure, if you want me,
or
I can just
something
read
additional.
out the question if that's helpful. So I just thank you for all your great work. I mean, obviously you took a really sophisticated deep dive into this question, but it does raise, I think, this issue, which is that I think it would be really easy for people to look at the final conclusion of your study, which is that annual wastewater costs might increase by about 4% by 2030, and just attribute that to setting the indoor conservation standard to 42 GPCD. But actually your modeling allowed urban suppliers to meet their urban water conservation targets through a range of options. It doesn't assume that they all end up at 42 RGPCD. So I'm really interested to hear whether in your model you projected most suppliers getting to 42 RGPCD or lower or higher, because that in turn would impact your projection for costs and impacts to wastewater systems.
Excellent question that's quite involved. Let me see. I'll try to answer it here. When we had to, so we ran out of time to fully answer your question, perhaps, would be the short answer. The more extensive answer is we were able to model baseline changes in indoor and outdoor use. And then, so in 2030, you can sort of model where you thought all the suppliers would end up. And that incorporated population change, the end use modeling that incorporated changes in technology from code, so improvements in fixture efficiency based on a lot of work that's already in literature. We didn't have to recreate the wheel. We also incorporated, which was something novel, what incentive-based rebates are being used, and what some assumptions around what suppliers are investing in because of other drivers such as cost effectiveness or something else like that. And so you put all these together and you get a baseline, and then, right, exactly as you say, the difference between the total volume of the objective and the total demand related to as best as possible that objective, that's the amount that has to be reduced. So we got to that point and we had those numbers, and our approach to evaluating what actions utilities would take was this, in economics, would be considered a least cost modeling approach, but it's essentially identify the costs and benefits of particular actions, sum them up, and then you have to just make the assumption in this case that they would undertake the most cost-effective route that sort of maximizes benefits or reduces costs. And that modeling really wasn't ready until basically the project was ending. I'll just be quite frank, because of the compressed time frame of putting this all together. So I have, credit to everyone on our team, but especially to Eric and Jonathan, who have been continuing to work since January on this to put this all together to get these numbers in order. And so the results of that analysis indicated that between 8 to 12%, depending upon your agency, would the reductions required to meet demand would be coming from the actions, including toilets and washers. And we were only able to model a set of potential options that are in the suite of typical conservation portfolios. So we looked at turf replacement, we looked at household leak loss detection separate than distribution systems, and we examined clothes washers and toilets. And we tried to benchmark this in empirical evaluations and industry standards and everything else. So we looked at the volumetric savings and the cost effectiveness that would derive associated with these actions. And then from that, what you're alluding to is that, yes, you could go back and identify where everyone is for indoor use. We didn't get there. You could do it in some more post-processing, but just to be completely honest, we can say where folks are and projected to be in their baseline, but not where they would be in meeting the objectives based on these assumptions. And it was only a portion of those reductions that would be associated with indoor use that would be associated with the 42 GPD standard. And I think I've noticed that it's been extremely confusing in all of the public workshops and trying to communicate this, that the standards are sort of being set according to, the indoor and outdoor and so forth. But we had to follow the rubric within the legislation to identify the economic effects and to be able to evaluate this for the state, which would mean that suppliers were able to kind of look at what options they wanted to do. And we certainly heard that cost effectiveness was going to be something that would be one priority as they look at the tools in the toolbox. So I hope that helps, and there'll be some more information, probably more details available at some point.
It does help. I feel like I could probably keep asking questions for another half an hour before I would completely understand, but I'll resist the urge to do that. But yes, I think that probably maybe like a simple FAQ or something to kind of elucidate this point to people would really help.
Maybe one thing worth pointing to would be the preface we uploaded to the website yesterday afternoon, and one of the assumptions that was made in this analysis, which was that when looking at the water savings, I'm going to attempt to explain this, and Eric, please jump in if I screw it up. But when looking at for each individual supplier, the amount of water that might need to be saved, under each scenario relative to their 2030 baseline. When looking at that quantity of potential savings, we assumed that 15% of the savings would come from indoor and 85% from outdoors. So I think that's maybe one of the simpler assumptions that we could sort of share with stakeholders as well. And I don't know if Eric, you could add anything to that or perhaps explain it more clearly than I did.
Yeah, it's a little bit confusing just because it's essentially related to the timeline of the project. So we had to submit the environmental impacts and make a lot of progress on evaluating effects on the wastewater community as well as trees and parklands. And so we made this 15% assumption. But that was based in kind of conversations and retailers. And then the actual economic modeling incorporated a least cost approach. So there was more flexibility for suppliers to choose. So the economic numbers indicate that if everyone just followed the least cost options, that they would pursue even less than 15% from additional indoor savings. And I think that's representative. It captures the dynamic we've heard a lot, that a lot of supply agencies recognize that it's getting harder to just bring people into conservation programs through sort of ready advertising. And so you're going to continue to replace and improve indoor fixtures up to current code, then you have to do some more outreach. And we didn't model toilets beyond 1.28 gallons per flush. So more efficient toilets. So more technology improvements could change that picture some for sure, but subject to the dynamics of when the existing fixtures would fail and so forth. So that's another, I think, important point of uncertainty. But generally speaking, more of the savings are likely to come from household leak detection and outdoor water use efficiency, even though those aren't necessarily, they have all sorts of, they have their own complications and costs and challenges associated with them.
It looks like Jamie would like to add something.
Yeah, I sort of related to this immediate topic at hand, but also to the earlier one. I think, we've seen a lot of challenges with the supply chain cost increases as a result of COVID and other just global phenomenon that is occurring. I think the supply chain constraints that we're seeing right now are really impacting project costs. And so the associated costs that are attributed to dealing with the impacts that we're seeing in the collection system and on-treatment plants maybe is understated, as we know that just normal materials, building materials, are increasingly constrained and then therefore more costly, and they take longer to build, which means the projects become more challenging as they move along. So I think that's another thing to consider, is that when we talk about COVID economics, it's not just demographic changes, and flow and revenue model changes. It's actually the normal products and inputs to construction projects have also changed costs since this study started.
Great, thanks for that context, Jamie. There's clearly a lot to cover here. This has been a very, very full day. Thank you everyone who has stayed on this long. I think we're gonna just answer one more really quick question from the Q&A, and then we will wrap for the day. So that question was, how will this information, assuming meaning everything shared today, be used during the rulemaking process? And if Charlotte, you want to answer that.
Sure. So Chris, in the beginning of this workshop, way back at 1 o'clock land, mentioned that the requirement that the Water Board consider, how the efficiency standards impact local wastewater management developed in natural parklands, and the health of urban trees be considered when we're looking at the proposed efficiency standards. And so these analyses that we've done in coordination with Eric Porson, the fabulous team here, are part of that decision-making process. We are providing this information to our board members, and they will consider the results of these studies along with a lot of the other material that we're developing as part of the regular rulemaking process. So when we do formally begin the rulemaking process, we will have an initial statement of reasons and a standardized regulatory impact analysis and a number of other documents that will be shared with stakeholders and with our board, who are the people that will make the decision on what the standards are. Additionally, the way that the CSU UC team approached this analysis was that it made it really easy, well, not really easy, but easier for us to be nimble and update our analyses because of the various models that were used to inform the analysis. And so specifically the wastewater piece of this, the estimated O&M and capital costs will be informing the standardized regulatory impact analysis. So those are the sort of two very fundamental ways in which this information will be used as part of the regular rulemaking process. And we really hope that additionally we'll be building on a much bigger conversation that has been happening in California for some time now about what do we do about these impacts that collection systems and wastewater treatment facilities and reuse facilities are facing as climate change advances, as regulatory requirements become tougher, as people begin to use water more efficiently, as we deal with PFAS and the universe of other issues that the wastewater sector is contending with. So I think I said in the outset that I think this is the beginning of a much bigger conversation, but I suppose that's not accurate, right? We're taking, this is just yet another step in a bigger and very important critical conversation that we're having as a state and how to adapt to a lot of the issues that we're confronting now. So 4:48, only, not quite an hour over. But yeah, just again, a big thanks for the entire group of panelists for joining us today, to SLO and Ventura for sharing your stories, for Jamie and Wyatt for, sharing your expertise and experiences, to DFA, and, to, of course, Eric and Harold and Caitlin for all your really excellent work and for all the attendees for sharing your time. So appreciate you all very much, and let's shut this down.
Yes, thank you again, everyone, for all of your incredible expertise and your participation, your engagement today. It's very meaningful to us. And check the website for our recording to go out probably tomorrow, and email us if you have more questions. So thank you and have a wonderful night.
Thank you, guys.
Thank you, everybody.
Take care.
Thanks, everyone.
Be healthy.
Thank you.
Okay, thanks, Vince.
Thanks, Wyatt.